want to introduce as to what we are going to learn as part of this device drivers 101 course. And this is, well, the Linux device drivers. This is supposed to be a D. Yeah, so Linux device drivers. What are we going to take a look at? First off, who this course is for? Students, early professionals, and anyone who is kind of looking forward to switch to device driver development, right? So this course is intentionally made for such folks, and we will only be covering the basics that you need to write a device driver, right? So absolute basics. And we'll also introduce what Linux kernel is, what device driver means, how it is useful, so on and so forth. Now, in terms of the tangible thing that you'll be introduced to, or you'll end up kind of authoring, would be these three files, and about the 4 to 5 lines of code here, 5 lines of code here, and maybe ballpark 60 to 100 lines of code in the C file. Now the C file will be the actual driver code, and the make file would be used to kind of compile that, and the Python file would be an application, right? So this is the device driver, this is the app. So what's the relation between app and the device driver? So we have the Linux kernel, which kind of has many device drivers within it, and one of them would be ours, right? And this is what we will author. But the user applications run at lower privilege, and that is where the Python file will be executed. So the Python file will serve as a user application, and what will happen is it will request the driver for some information, and the driver will essentially pass back that information, right? And in this kind of a mini project like way, we'll end up learning what device drivers are, and how to write those, and understand like the background and the mental models in terms of how the Linux kernel works, how the driver has to work, and how to add functionality, right? So this being the case, let me just go ahead and quickly show you a demo of what things will look like. And let me go ahead and increase. Very nice. So what you see on the screen here is let me just, yeah. So this here is essentially the code, and the code to what? This is the user application. This is the make file, which is like 7 lines of code or something. And then there's this device driver, which is about 60 lines of code, right? So then let's go ahead and take a look at this Python file here, the user application. It simply kind of opens a file, reads a file, reads some message, reads like a line out of it, and closes the file. So 3 simple operations. Let me go ahead and do make. This is like building the device driver, and then let me do sudo insmod, sudo insmod .ko, and then let me go ahead and kind of execute the app. And the app is user space app. And so what you'll notice here is it's simply going to count the number of times the call to the driver was made, or the driver was activated, essentially, right? So let's then go ahead and execute this couple times, and what you see here is with every call or execution, this number is increasing. So this somewhere is that mini project, or project based approach, wherein we'll go ahead, write a device driver, and then write a user app to interact with the device driver. And along the way, we'll learn how to write a device driver, what are the basics, how to inject it into the kernel, how the kernel absorbs it, how the interactions go, and all of that good stuff. At the end of this course, Our hope is that you'll be enabled to understand the language of Linux device drivers, the vocabulary associated with it. To some degree, of course, it's like a vast subject, but you will be able to make sense of what device driver related jobs are, what they require, and how to self navigate in the future. So, with all of this, if this excites you, I'll see you on the other side. All right, so let's briefly discuss as to how we are going to go about learning device driver development, and in terms of the environment and the setup that we need. So first, let me pull up my whiteboard or blackboard here, and then let me explain you what we intend to do. So we need a Linux environment or Linux operating system to be able to do Linux device driver development, right? Now, what we are going to do is, as you can see, I'm on a Mac, right? You might be on a Mac, Windows, or Linux. Now, even if you are, let's say, on Linux, we would recommend that you follow the steps that we are suggesting so that you can protect your own current operating system from let's say accidental damage, right? We don't want to corrupt any file, don't want to accidentally hurt the operating system. So now what we are going to do is create an environment for ourselves, right? Which will have the Linux OS running within it. And we are going to do all our driver development and experiments here, right? And my proposal is that we will create this environment within the operating system that you're on. For example, it could be on a Mac, on Windows, right? Or even Linux, right? So what we want to do is create this environment that kind of runs the Linux operating system, and within that we'll develop the drivers. The other thing we want to do is, because we don't want to end up working in the terminal always, we would want to write code in some files and so on and so forth. We are going to use VS Code, which is running on whichever OS that is your parent or host OS. So VS Code is running on your parent OS, and we connect to this Linux environment right here over SSH. The idea then would be that whatever files we want to, or whatever code we want to develop here, we can actually use VS Code to do that code development or write that code. But the files are being created, the code is being written and committed to the files which are on this Linux environment. This Linux environment will call a virtual instance, right? And then the software that manages this instance, we are going to use like a virtual instance manager, or more formally called a hypervisor. Um, we're going to use a hypervisor, and that the name of that hypervisor is multi-pass, right? So multi-pass is like a beautiful command line utility that can do the environment setup for you. You don't have to execute too many commands. And so what I now propose that you imagine going forward is, we are going to develop code within a Linux operating system environment, and we are going to connect to that over VS Code, and the Linux operating environment itself is running on top of, or is managed by, a hypervisor called multipass, right? So the upshot here now is, if we do something bad here, or screw up, or put this Linux image in a bad state, we can just discard all of this and respin or recreate another instance. In that case, we would not be hurting or screwing up any of your parent or host OS environment. Hopefully this is clear, that we are just wanting to create a sandbox for ourselves to work in and try out the experiments. And in the next videos, what we'll do is, we'll go ahead and take a look at how to do the setup on Mac, Linux, Windows, and then after that we will start to write code, understand different parts of how the device driver code is, and so on and so forth. So as part of this video, we are going to take a look at how to set up the multipass and kind of create a Ubuntu Linux image instance on your Mac. Right. So the first things first, what I'm going to do is launch a terminal. We are going to use this in a while. And quite honestly, I already have multipass installed, but I'm going to follow the steps anyway so that you can also follow them through. All right. So we're going to open up Chrome, and then we are going to type multipass, and the first link that comes up should be multipass.run, and we'll then just go to multipass website, and here we'll go into docs. Within docs, go to how to guides, and within that go to install multipass. Now come to check prerequisites, or rather, sorry, come to install, and then go ahead and select Mac OS, and then all of a sudden, things show up here. Now you can use an installer package. That is not what I have done. You can go ahead and do that. I'm using Brew, and so let's open up a new tab. And so the command then is brew install multipass, right? And this is where I go back to my terminal and simply paste here, brew install multipass, and then hit the return key. And this will then go ahead and install multipass for me. Now what can happen is if multipass is not getting installed this way, um, uh, let me just show you what you can do. um, uh, okay, all right, I tried out multipass just too many times. There has to be a command which I must have used. Okay, just a moment. Hmm. Okay, so what you can do is you can do brew install minus minus cask and then do multipass, right? If you have brew installed and you want to install multipass, these are the two ways. Either go ahead and just use brew install multipass. If not, then use brew install minus minus cask multipass. All right, so we at this point then have multipass installed. Great. And what you see on the screen here is when I type multipass right here, it goes ahead and prints like the help options, right? Yeah, it prints the help related data. One more thing here, if you don't have Brew installed on your Mac, go ahead and follow this link, which will kind of, tell you how to install a Brew, and then you can go ahead and use, this command right here, and then follow the steps essentially. All right. So assuming that things work out good for you until this point, what we're now going to do is create that instance within which we are going to work. And let me then quickly uh, bring up the Blackboard here and remind you of what we were planning on doing. We said that, hey, this is our host machine or host operating system, could be Mac, Windows, right, and Linux, or Linux rather. And right now we are on a Mac. So this is our Mac host. And what we did was install multipass, which is the hypervisor or image instance manager, virtual machine manager. And we also said we would have VS Code here, and we want VS Code to connect over SSH. And then there has to be some instance running here. Right now, we don't have that instance. Right at this moment, we only have multipass the software, and what we are next going to do is ask multipass to create that instance for us. So we are just going to type multipass and then say, okay, also let me increase the font size a little bit so you can. All right, let me just. Okay, so we are going to type multipass hyphen shell. That's about it. And what it is now doing is it is kind of preparing, the primary instance. What it'll do is download some image, prepare it in the background, and then actually drop the shell or terminal for that instance. And we'll see that happening in a while. This should kind of, depending on the internet speed, this should take anywhere from few minutes to tens or maybe even an hour if your internet is slower. On my machine, this is like pretty fast, and yeah, almost done. So it has launched the primary here. It is kind of setting up some few things in the background. And once all of this is done, it will print like the details and then drop the shell. So let's just wait for that. All right, perfect. So if you see or notice here, it says, "Hey, welcome to Ubuntu 24.04, blah blah blah, all of the details." This is something of use to us, the IP address, and we'll come to this in a while. Uh, but now, what we intend on doing is we are within the multipass instance, so to speak, and we are supposed to now execute few more commands just so that VS Code can properly connect with the primary instance. Primary is essentially name of this machine, right? And so primary instance, we want VS Code to connect to it. So I'll go ahead and modify a few files. So let me copy the command and paste it here. So this command right here, the sudo space vim space slash etc slash ssh slash sshd underscore config, we are going to edit this file slash etc so on and so forth, right? And we are wanting to edit this file just so that we can enable password based login into this system. All of this will make sense in a minute. So I'm within that file now. I'm going to type a colon set space nu and hit the return key. Once I do that, you can see the line numbers are enabled, and we are going to go now to line number 62, right? Line number 62 is this. So this is for keyboard based interactions, right? Interactive authentication. Now I want to go ahead and edit this no right here, this thing right here, this no to a yes. And to do so, to edit a line, what we are going to do is first come to that line, come to that point. So I need to come to, no, the N, and then hit the I key. And as you hit the I key, you will see that, Vim, the editor, goes into something called the insert mode. Then I will go to the end of no, delete it, type yes, and after that, hit the escape key. Once I hit escape key, Vim comes out of the edit or insert mode, and it's now in like the command mode. What I'll do now is type colon WQ and hit the return key, and it writes the updates to the file, right? Now, again, why did we do all of this? It's just because we do not have a GUI, we do not have any visual interface, or we cannot use like any other text editor to edit this. You can use Nano or any other command line editor if you already know of, but Vim, something I know kind of decently to be able to edit files. So I have used that. All right, so the edits are made. Now what we are going to do is kind of ask the system control to kind of reload its daemon. And so let me then go ahead and execute this command, which is sudo systemctl space daemon hyphen reload. Right. Once that is done, we'll go ahead and ask it to restart the SSH service so that remote connections are possible. Again, sudo service SSH restart. And then after that, we are going to do, set a password for this user. Now, the user on this machine is Ubuntu, right? And so Ubuntu at the rate primary means primary is the machine name and Ubuntu is the username. So we are now going to kind of type this command sudo passwd Ubuntu and or Ubuntu, and that essentially is like, hey, set a password for Ubuntu. In my case, I'll just set the password to lowercase p, and whatever you set the password, just be sure to note it down, and that's the password you have to use going forward anytime we want to log in into this machine, right? Log in or execute the sudo command. All right, so we are good now. We have prepared our instance to be able to be connected through SSH. So now I'm going to go ahead and pull up VS Code. And if you have VS Code, then once you open VS Code, go to the extensions. And then from there, if you don't already have it installed, type remote and install this remote development. Let me just pull up the marker here. So install this remote development extension, right? I kind of have parts of it installed. So let me, go ahead and install that. Once you install this icon should kind of become visible, right? In my case, I had few parts of this package already present, so that's why I already had this. But you should, if not already, if you don't have the remote extension already installed, you will see this as a new icon, right? And once you see this, click on that. And I already have some SSH related things here. Go back to our terminal, type if conf, oh sorry, not that, type host name hyphen uppercase I. And the moment you do that, you'll see that the IP address is printed here, which is 192.168.64.12. Copy that, right? Come back to VS Code, go to this SSH related, drop down right here. And if you don't see this drop down, be sure to select remote, tunnels and SSH here, right? In the remote explorer, select remotes and tunnel slash SSH. And then within the SSH drop down here, click on this plus button. And once you click on the plus button, like a, user input panel pops up. And in that, you write Ubuntu at the rate and paste the IP address, right? So we are saying, hey, log into this machine 192.168.64.12 as Ubuntu the user, right? And we hit return key. And once you hit the return key, it'll ask you like where to save this config, just hit the return key again. And we have added details of the remote machine. Now we should have seen it here. We don't, so not a thing to worry about. Go ahead and click this refresh button, and the moment you click this, you'll see that the IP address is visible here. Now what I want to do is ask VS Code to connect to this instance, right? So let me, to show you the magic now, let me just take VS Code on the left side and our machine, the primary instance, on the right side. Okay, so I'm going to go to this option here, 192, 168.64.12, and click this arrow button, which says, I would like the current window of VS Code to attempt a connection, a remote connection to my instance. And let me go ahead and do that. Now, what I'll also get myself out of the way. It's saying, hey, do you want to continue? I'm saying yes. Then it asks me for the password, and this is the password that we set. I'm going to type P because that was the password I set. You can set some other password, but use that password here. Now at the bottom here, you'll notice that it says, hey, SSH colon 192.168.64.12. And if that has happened, then it confirms that the connection is established. Right. Now we're going to do some experiments to prove our point that, whatever edits we make in VS Code are actually happening within our virtual instance or virtual machine here. So let me go ahead and execute ls, and then let me type kind of, mkdir ldd. So we are creating a directory which is LDD, and within that we will work. So let's go into LDD, CD into that, and we see there is nothing here. Perfect. Now we come back to the VS Code and say open folder, right? And when we say open folder, you'll notice that LDD is available here. So this is a hint that we are actually looking inside the file system of the instance that we have created, the primary instance, or the instance by the name primary. So click on LDD here and click OK. What we will notice now is right here, it's saying it's on LDD directory within and it's on SSH on 192.68.64.12. All right, we'll go ahead and now click this new file button and call this file test. Right, and we'll go ahead and write hello world into the test file. Now, because we are making all the edits on VS Code, which is connected to our virtual machine or the Ubuntu instance within multipass, if I execute ls here in the terminal, you'll notice that the test file was created, right? And the file we created was in VS Code. All right, so now if I were to do like a cat test, we'll see that the hello world is available here, which is the content of the file. So let's just quickly revise as to what happened here. So we had, primary, uh, and primary was a virtual machine that multipass created. And within this, we created the LDD directory, right? And we also said that VS Code was over SSH connected to this machine, right? And so what we then asked is opened LDD in VS Code and then added this file test, and the content of which was hello world. Right. And so this hello world and this test file all of a sudden appeared here because of this SSH tunnel or connection. And then within that, we saw that, hello world is available. So what we are going to do is, hide this window going forward and only work within the VS Code environment, and also connect or kind of create a terminal, that is same as the terminal in our virtual machine. And so this way, VS Code becomes that nice isolated environment wherein we can develop our code and try out our experiments. So in the videos following this, we'll explore, which part of driver is what files to write, what part means which, and so on and so forth. All right, so in this video, what we are going to do is take a look at how to install the multipass on a Linux machine. Now, as you can see, I'm on my Mac, but I have a remote Linux machine that I'm going to log into. So let me just go ahead and pull that up. So this is our Linux machine, and what we'll do is follow the steps to kind of install multipass in here. So the first thing I'm going to do is, launch a terminal. So, launch a terminal. So I have a terminal. So I'll need this in a while. And then I'm going to open up my Firefox browser. And once I am here, I'm going to write multipass. So what we are intending to do is look up the steps to install this. So I'll straight up go to, multipass's website and accept all the cookies because I don't care. And somewhere there has to be documentation, and within documentation there would be I think it's the how to guide install multipass. Somewhere I need to go check multipass for Linux. So this command is for Linux right here, and we can go ahead and choose other OSs, but Linux is what we are after. Okay, so I'm going to get this aside, and we have the terminal here. Let me go ahead and paste that on terminal, and know that we will need to use sudo here. Sudo snap install. I give my password, uh, and then we just wait while it installs. There's there is like a level of satisfaction. It's an odd satisfaction that at least I get by looking at the progress bar make progress, and we are almost done. Now, of course, the download and install time depends on your network speed. And let's see, should install it now. Done. And something happened. Okay. So the remote connection disconnected. So let me log into my machine again. As luck would have it, Murphy's Law in action. So let's see what's happening. My remote machine doesn't seem to cooperate. Why? Okay. Welcome to live debugging. So the first thing we do is, okay, force quit. Oh, it's not responding. Let's force quit it. Yes, of course. All right. So I'm going to bring up the remote connector. Let's see. Yes, we are back in business. All right. Sorry for the disconnection, but now we have multipass here. And what we are going to do is multipass list. We don't have any instance, which is perfect. And now I'm just going to do multipass shell, right? And again, we don't have to do all of the multipass thingy. If you want to, you can just start development on the Linux machine that you have. But the thing is, with driver development, there are chances that we might do something, stupid and screw up the kernel, or put it in like a bad state. To avoid all of that, we are using multipass. So we have like a nice sandbox environment within which we can develop our driver and install, try out different experiments. And even if we screw up, well, then the multipass environment is what we have screwed up, and we can always create another instance and then screw that up. So that is the reason that we recommend using multipass. And as we can see, it has retrieved the image of Ubuntu, and it is going ahead verifying that image, and then it will like create an instance and launch that instance. Let's just wait for it. Yeah, almost done. You can skip forward if you'd want, or just listen to me blabber and talk shit, kind of. Yeah. All right, we'll just wait. This is like almost done. Yeah, I can tell. It's almost done. In the meantime, can I go ahead and maybe let's see. Let's launch VS Code. So we have VS Code here. Let that come on the side here. Perfect. So what we will need also to connect VS Code to the multipass, and let me just very quickly draw a diagram. So what we are intending to do is we have our host machine, right, within which we will have and let me actually also go ahead and do this. Yeah, so within which we'll have the multi-pass, right? And so there is a Linux image running here. And now what we intend on doing is, connect, or rather there's like a development environment here. There are some files and all of that. We will be developing our driver here. What we want to do is take VS Code and connect it to this so that we can develop here and the files get generated here, right? We kind of want to do SSH into this. And for those reasons, I launched VS Code. All right, so in VS Code, then what we're supposed to do is go to the extensions here and install the remote. Yeah, let's just type remote and remote development. So we'll just install this. So while this installs itself, let's go and check what happened here. All right, perfect. So it went ahead, created the primary instance named primary, and it also went ahead and kind of, launched it. So if you see now here, Ubuntu at the rate primary is what we see. Now we are supposed to, carry out few steps here, which will allow the VS Code to connect to the multipass instance. And so we are going to execute set of commands now. And the first command, let me just copy it from a different, uh, you know, file. So the first thing we'll do is allow SSH authentication using the keyboard interaction, right? So, okay, I should have talked about it, but I did not. Just a moment. Yeah, so this is the file that we want to edit, the /etc/ssh/sssd_config. And then within this, Let me just type colon set space nu, which kind of enables the line number, and then we'll search for password, and let's go next. So line 62 is essentially, what we want to change, and change it to a yes. By the way, if you find yourself not able to enter the characters here, the vim command, you can press I to go into interactive mode. Then you can edit things, and once you're done with the edits, hit the escape key to come back into the command mode, and then hit colon WQ. Of course, you can use Nano or any other command line editor that you're aware of. This is what I want to use. So set line number 62, this option here, to yes, right? And so we get rid of this. After we have kind of edited the file, we will execute this command, which is we are asking the daemon to reload. So this has happened. Uh, and then what we'll do is restart the SSH service. Let me go ahead and do that here. Um, right. And so service is restarted. And then the next thing we want to do is we don't know what the password for this user Ubuntu is. So we're going to set a password. By default, multipass doesn't set a password. So we are going to do that. And we're going to execute this command, which is sudo uh, pass wd space the username, which is Ubuntu, and then we hit enter. The new password, I'm just keeping it as lowercase p in my case. You can keep whatever, but whatever password you set is the password you will use going forward. All right, so we have successfully carried out all the steps. Now, the other thing we want to do is get the IP address of this, right? So type host name hyphen, uppercase I, and this is the IP address that we are going to use. Now, at this point, let's return back to our Blackboard, and then this was our host machine on which we are installing the multipass and all of that. This is our primary machine. Right? And then this is, let's say, our VS Code, right? So VS Code is running here, and this itself has an internal IP, whatever that number was. What we're going to do is ask VS Code to reach out to that IP and set up an SSH tunnel, right? And we also installed the remote dev extension here. And using that remote dev extension, we are going to ask, hey, connect to this IP address, and then it will form a connection, and then we should be able to see the files here, right? And let's then quickly take a look at how we do that. All right, so this is the IP address. Let's copy it, then go to our VS Code, and here we will see this remote explorer, right? So what we want to do is go to remote explorer, be sure to change the dev containers to remotes tunnels slash SSH. And once we are there, then go ahead and against this SSH right here, click on new remote. So once the new remote is enabled, or this kind of tray pops up, I don't know, tray or some user input related panel pops up, type Ubuntu, which is the username for the primary machine, and then add the rate, and then go ahead and paste the IP address. Then hit the return key, and then add it to like the .ssh/config. Everything's great. What we're going to do is move this aside, close this. Let me put it back here. Let's close this as well. Then hit this refresh button here, right? And the moment you hit refresh, you will see the IP address right here. Now what we'll do is say, go ahead and connect it in the current window, and let me get myself out of view. Notice what happens here. So once I go ahead and hit, connect in the current window, you will see that VS Code is trying to establish connection. It is asking me, should we continue? I say yes. Then it asks me for the password, and this is the password we set, in my case, P. So once I put the P and hit return key, it establishes a connection. And once the connection is established, we should we should quickly see, we should see this change to the remote IP address. That should happen anytime now. Right, perfect. So here we say we see that the remote IP address is seen, which means now VS Code is connected to the primary instance of multipass. And let me now get this out of the way. Let's go ahead and put this on the right. Okay, so now I'm going to try and open a directory in VS Code, which is, the directory is again on the primary machine. So first off, let's do an ls vc home and vc snap. What I'm going to do is create a new directory called ldd Linux device driver, right? And when I now get into it, there is nothing right here. Now I go back to VS Code, say open folder, and all of a sudden I see here LDD. And LDD again should reinforce the notion that VS Code is actually connected to the primary instance, and we are seeing a view inside of the primary instance, right? So I connect to LDD and say okay. And once I've done that, okay, it's kind of now asking me if I trust. Yes, I trust the authors. The author is I or me, or whichever is the correct usage. All right. So now we don't see any files here. Let me go ahead and create a test file here, which kind of, let's say, has hello world. This is just us, trying to confirm. And let me go ahead and save it. And now I come back to this terminal, say ls, and I see test. And when I do cat test, I should see hello world, right? Same exact thing as here. So this hopefully should convince you that we used multipass to create like a sandbox environment, a virtual what do you say, a virtual box kind of an environment where we have the Ubuntu operating system running with Ubuntu as the user, and this machine's name is called primary. And what we did was followed through some steps to allow VS Code, which is outside of the sandbox environment, to connect to it. And any experiment that we do now will be within this primary instance, which is a virtual machine, which is a sandbox. And again, just to reiterate, we did all of this song and dance just so that we have a sandbox environment in which to write our code. And if we screw up and do some damage, the damage is not going to happen to your machine, not to your operating system, but to the sandbox. All right, if you are able to get to this point, congratulations. You and I are at the same level now in terms of trying out experiments, and I'll see you in the next video. All right, so as part of this video, we're going to take a look at how to set up a working environment on a Windows machine. Now, what we want to do is create a sandbox within which Ubuntu can run, a Linux image can run, and this sandbox is essentially a virtual machine. And we want to use VS Code to connect to this virtual machine so that we can write code in VS Code, right? And towards this end, then there are three softwares that we'll require. One is called multipass. So multipass is the software that will manage that virtual machine for us. It will create and manage that virtual machine. So we go to multipass's website and okay, accept all the cookies, go to the documents section, the docs option here, and then go to how to guides. And then within how to guides, go to install multipass. Once you're there, scroll down and check the prerequisites section and click on Windows. Now, what we notice here is multipass uses a hypervisor to essentially create and manage an image. right? And so the hypervisor in our case, at least in my case that I wanted to use, was VirtualBox. And the reason to that is the Hyper-V only works on Windows 10 Pro and Enterprise, and I have a Windows Home installation. So I'm going to go ahead and focus on the VirtualBox. It says Multipass also supports using VirtualBox as a virtualization provider. You can download the latest version from here. So I'm going to right click this and open it in new tab, and then go on this tab, scroll down and download it for the Windows platform. Now it is asking me to save. I will save this, and it has downloaded it, so I just launch it, right? So the installer for VirtualBox has launched, and what we would want to do is essentially install VirtualBox. All right, so next, yes, install. So as VirtualBox installs here, I'll go back to the main page and then proceed with, download the latest installer of what? Multipass. So installer of Multipass would be available on their download page here. I just click on it and it should go ahead and straight up download Multipass. So it's asking me to save that executable. I will save it, and it should take another second, and Multipass is downloaded. What I'll do is click on that and also launch the Multipass installer, right? And let's go check. So VirtualBox is completely installed. I don't want to launch it, so I uncheck this option and click finish. This is the installer for Multipass. I'll go ahead, agree to the terms, and okay. On this page, if you see, it says, hey, what hypervisor should I be using? So we say Oracle VM VirtualBox. This is why we required VirtualBox. Now, okay, then we move ahead, and I like to install for all users, and the users path variable. So next here, next, next. Yeah, it's installing. This takes like a while. Now, the third piece of software that we need, if you don't already have it installed, is VS Code. So I'm going to download and install VS Code as well. Right. So I go to the VS code.vs code or code.visualstudio.com, and there I see this big button which says download for Windows, stable build, and I just click on that. Once I click on that, the pop-up pops up asking me to save the binary file, the executable file, and VS Code is also downloaded. So I'll go ahead and also start the installation of VS Code. Uh, Go ahead and do next. Yes. Uh, yes. I like to also have open with code as an option. So I will check those and install. In the meantime, here Multipass has finished installing. All right. So we got the virtual box, we got the Multipass, and we also have VS Code getting installed right now. So the next step that we want to do, the next thing that we want to do is create that virtual machine, that sandbox environment using Multipass. So to be able to do that, we click on the start menu and then type CMD to launch a command prompt. And then I see command prompt here. I just click on it and launch the command prompt. Let me go back here once and say, don't launch VS Code, just complete the installation. We also don't need the browser anymore. We only need this terminal window. Now, what we plan on doing is create a virtual machine by the name primary. And the reason we want it to be named as primary is for the Mac and the Linux users, the default machine that gets kind of created is called primary. So we wanted the environment to be constant across different operating systems, and that's why we will create a machine by the name primary. All right. So on Windows machine, we had been having some problems in terms of assigning an IP address to the virtual machine. It was not automatically taking that. And so we will need to type this command multipass networks, and it will give some network information. And the name of the network is what we want. and I'll show you the command shortly. But all right, so it prints various networks that are available, and the network that I'm on or is available in the interface that's available is by the name Wi-Fi. This name here is what is of use to us. If you have multiple of these, pick any, things should work fine. Um, I would recommend using the one on which you have an active internet connection. Right. Okay. So we have the name Wi-Fi here. Now let me pull up a command that we need to copy paste to be able to create this instance. And that command is this. So multipass space launch space hyphen hyphen network space Wi-Fi. And this name has to be exactly the same that you have here. It might differ for you, but whatever that name is, that's what needs to go here. Space hyphen hyphen name space primary. And this is how we are naming our instance by the name primary, right? And again, the history of this is Mac and Linux users have the machine named primary. We wanted it to be same across all three operating systems. So for those reasons. All right, so I'll copy this and paste it here and fire this command. And what this should do now is download the Ubuntu image, right? It is retrieving an image from the internet, and it'll create that instance with a predefined configuration. I suppose it is 5 GB of disk space and 2 GB or 1 GB of RAM, something like that. And it will create that instance and then in the background start it. Right, so we just have to wait here now for the image or the instance to be created. This kind of takes a while, and just to avoid any editing of the video, I'm kind of not going to skip any part. So this will take a while. So maybe in the meantime, I'll talk about what we plan on doing next. Right, so next for us is, so what we want to do is first off, set up the primary machine to accept SSH connections using password, right? So we want to enable password based authentication to be able to SSH into that machine. The reason that is necessary is, if not password, it will kind of look for RSA key, uh, public private key pair. It will kind of go in that direction, and we don't want that. That is too complicated for us. Makes life a little more complicated. It increases the number of steps. We didn't want that, so we have to enable password based authentication. So we'll do that, and for to be able to do this, we need to kind of edit few files. Well, edit a file and restart few services, right? So we'll do that once our instance is active. The second thing we want to do is connect VS Code to primary over SSH, right? And for this, we will need to install an extension on VS Code, right? So this is the second thing. All right. And then on this primary machine, we will need to also set a password for the user Ubuntu. So Ubuntu is like this default user that multipass creates on the virtual machine, and this user doesn't have a password. So we'll need to set a password. And again, let me just type it down here. So this is on the primary instance or machine, and this is on Windows, right? So while this is loading and getting, setting itself up, what we can do is we can go ahead and install this extension for VS Code. So VS Code, we'll just launch it from here. And once, okay, this is from the previous instance. So ignore that. What is this? We don't want it. Restricted mode, internet for safe. Okay, fine. So we go to the extensions here, and we will look for remote. And the moment we get options, look for this remote development and extension pack. So this extension pack has many more extensions that it installs to be able to enable us to work with a remote machine. And this instance of Ubuntu, the primary machine, that will act as a remote machine that we log in into and develop the code using VS Code. All right. So we only need the remote SSH and remote explorer, but it's a good idea to kind of go ahead and install all of the extensions as part of the remote development pack. All of these are installed, and now we see that this remote explorer option is available to us. This icon is available to us. Just click on that. I will need to, well, I had created this earlier, so it is picking up from like the previous installation of VS Code from some cached files. So let me actually pretend that you have not seen this. Okay, so all right. So cool. All right. So you should see something similar to this if this is your first time working with a remote machine. And what you have to ensure is that you are within this remotes tunnels slash SSH option. Be sure to be there, and then you will see that within this SSH there is like nothing or your previous machines if you already work with SSH on remote machines. Now let's go back here, and what we see is that uh, it has kind of launched the primary machine here, and we'll type multi-pass list, and when we see the results here, we'll notice that IP address is assigned to our machine. The name is primary, and it is running Ubuntu 24.04. Right, perfect. So now what we want to do is visit back and complete these steps here. We are done with these steps here on the Windows side. We want to go ahead and now make those, edit those file, allow the password based authentication, and restart the SSH service. So the way we get inside the machine, the primary machine, is we say multipass shell. And shell by default, this command will essentially get us into the primary machine. So I have hit the return key, and right. So if we see here, it prints this long welcome message, and then drops the prompt, right? And if you see, Ubuntu is the user, primary is the machine name, right? And as I was saying, the installation, it kind of had 4 GB of disk space used up, and it kind of, I think, has 1 or 2 GB worth of RAM, right, as the usage. So what we are now going to do is edit few files using vim. So type sudo vim. Vim is a command line editor, a file editor, and we then say /etc/ssh SSH, and within that sshd underscore config. This is the file that we want to edit. So hit return. Now, the way Vim operates is that it has something called command mode and insert mode. Insert mode is when you can change the file, and command mode is when you can essentially save it, undo things, delete things, so on and so forth. Right now, we are in the command mode. So using our cursor up and down arrow, we can go, scroll up and down. But what I want us to do is enable file numbers, line numbers. So type colon, and you can see it types the colon here, and that's the command. So colon is like a queue that a command is starting, right? And then we say set space nu, which is set line number, and when you hit the return key, you see that the line numbers are enabled. Now we'll go down to line 62, right, which is right here, and it says a keyboard based interactive authentication. It's set to it's essentially disabled, and we want to enable it. So go to the no, and then hit the I key. And once you hit the I key, you'll see that the Vim has changed to insert mode. And now if we type something, it will actually type in the file. So we are going to now delete the no and type a yes. And we want to now save this one change. So the way to save the change is to hit the escape key. So we go from insert mode to the command mode again, and now type colon WQ, which is write this file to the disk, write the changes to the disk, and quit the program, right? So the changes are now made. What we now have to do is reload the daemon, the system control daemon. And so we'll say sudo systemctl daemon reload, right? And hopefully this works. Yes. So the system control daemon is now reloaded. And now we say sudo service ssh restart. So we are now saying, hey, please restart the ssh service so that the settings take effect. All right. So we are now done with allowing password based login or password based authentication. Now what we want to do is set the password for the user Ubuntu. So the way we do that is say sudo passwd space Ubuntu. And now it says, hey, enter a new password. And I'm going to just use my password as the alphabet P, lowercase p. So P, enter, the new password is set. Perfect. Now what I'm going to do, just so that we understand that VS Code actually could connect to this machine, what we are going to do is create a directory called LDD, which is Linux device drivers. And now if I do ls, there is a directory available, LDD. Perfect. I'll go within LDD and stay there. There are kind of there are no files within LDD. It's completely empty. And we'll come back to this in a minute. All right, perfect. So our virtual machine is all set. All configurations are done there. Now what we want is we want the IP address of this machine, right? And we can then go to a new tab here and again type multi-pass, list, and recall that it was also printing the IP address, right? So we got the IP address. Perfect. Copy that, go back to the virtual machines terminal here, come back to VS Code, and now in this SSH option, click this plus button. Now it's asking us which machine do we want to connect to. So we say, hey, connect using the user Ubuntu on this IP address 192.168.0.199, and we hit the return key. It says, hey, where do I save this? We say, hey, save it in the config file, the first one. And now it says, shall I go ahead and connect? All right. So ignore this for now. Come back here, and there is this refresh button on the remotes, tunnels, all of that. So click the refresh and you will see the machine's IP available here. Now what we want to do is go ahead and click on this button which says connect in the current window, and it will start to connect to this remote machine. We say the remote machine is running Linux, right? And do you want to continue? Yes. Enter the password. The password is what we set for the Ubuntu user, which is P in my case. Whatever you chose as the password, just enter that. And here now, if you see at the bottom, it says opening remote. So it's trying to connect to that remote machine. And remote machine in this case is the Ubuntu virtual machine that we are running. All right, it should be almost done. Almost there. So the IP address of the remote machine will show up here once it has kind of, set up the connection with the virtual machine. This should take a few more seconds. All right, perfect. So if you see here now, 192.168.0.199 is the IP address of our virtual machine, the Ubuntu machine that we created using multipass. And now it has connected. What we want to do now is open up a directory to work in, and this directory will be on the virtual machine. So go to the file explorer here, the explorer, and open a folder. And when you kind of see here, there will be LDD listed, and this should convince you that we created LDD within the virtual machine, and VS Code is right now peeping inside or looking inside the virtual machine. So we open up LDD and hit OK. So it is going to kind of reestablish the connection. So it's asking Linux to be like the operating system running on the VM, asks for password, I enter P, we again wait for it, and it should go ahead and establish this connection. And it's now saying, hey, do you trust the author of this code? And we say yes, and now we are connected, right? Now, to prove a point that how we can go about developing the code in VS Code and running it elsewhere meaning within the virtual machine, we'll go ahead and create a new file by clicking on this new file button, and let's call it test.txt, right? And let's just type in hello world within that, followed by a new line. And now let's go back to our terminal here. Notice when we did list here, executed the ls command or the list command, nothing showed up. But now when I do list, test.txt shows up. So you should be now convinced that we were editing in VS Code, but the files were within the virtual machine. And what we are now going to do is essentially, run the cat command, which essentially prints the contents of the file, and the contents are hello world, right? And that is also what we see here. Perfect. Now here's another thing. If we open up this terminal option or menu and go to new terminal, then the terminal that appears here is exactly the same that the terminal that appeared here, which then means that the terminal here is actually of the virtual machine, right? It's actually peeping into the virtual machine, also giving us a view from of the virtual machine. So we then do not need this terminal anymore, and this is now our complete working or our development environment. We can run all our experiments here, develop the code here, compile it here, and also try running it from within the terminal that's available here. So if you are at the same point as I am and everything's working just as it is on the screen for you, congratulations, the setup is complete. And next time on, whatever development we do will be within this directory and in this format. Perfect. So with this, I'll see you in the next one.
Hey there. So as part of this video, what we are going to do is kind of see how to start multipass if you have rebooted your system, or you have closed the terminal, or you know you've exited the VS Code environment. So we'll take a look at how to go about reinitializing or respawning or restarting the instance, the primary instance that we had created. So let's pull up a terminal. And by the way, not only that, we'll also talk about what the prerequisites to be able to compile a Linux kernel module are, and we'll kind of set up that environment. Okay, so what you need to do then is pull up a terminal and type multipass. Now, once you do that, multipass essentially presents the help options, or different options that are available, and we are going to use the list. So let's do multipass list, and we see that our primary instance here, the instance we had created as part of the setup videos, that is available, and it is in the stop state. So what we are going to do to launch it again, to activate it again, is simply type multipass space shell. That's enough. Once we do that, it will start the primary instance again, and much like the previous videos, drop the prompt, or get us into the terminal that's within the instance. So this should take like a while, and once it's done, it will present to us the terminal that is within the primary machine, or this virtual machine that we have created. So let's just give it like few more seconds, and here it is. So now, as it starts and drops the prompt for us, it has printed all of these details, and among which is this IP address, which is of use to us when connecting over VS Code. Okay, so now the virtual machine or the sandbox environment or the primary machine that multipass is managing is activated, right? So the next step is we are going to go and much like previous video, connect it to VS Code. So let me pull up VS Code and then just to revise, we go to the remote extensions option here on the left side, click on that and then look for the IP address of this machine, which happens to be 192.168.64.12. And as of previous video, we had connected to this directory LDD where we mentioned we will run all our experiments. So let's go into VDD and it asks us for the password. So let's press the password, add the password and hit return. And you can ignore all of these files for now because I have added those in while doing some experiments offline. So ignore those for now. Let's close everything. And here in the Explorer view, we see all of this. Well, you might not see this, but let me kind of, select one of them and then slowly select all of them and delete them. So that's where we want to be, a clean directory. Now what we are going to do is kind of crucial, which is to be able to take our C code and compile it into a kernel module. We'll require some utilities like compiler, some header files, all of those. And to be able to ensure that you also have those utilities, what we are going to do is simply kind of click Control and the tilde key to bring up a terminal here. And this terminal, okay, let me zoom this in also. So this terminal is same as the terminal we have here, right? So we see Ubuntu at the rate primary here, and we see Ubuntu at the rate primary here. So the terminals are same. Now what we're going to do is we're going to install some utilities that are required to be able to compile the code into a loadable module. And to be able to do that, we're going to execute these commands here. So let me copy those and in a new file, put it right here in front of us. And let me just go through each one of them one by one. Uh, so what we are going to do is the first command here is essentially saying that we want to update the lists of a package manager, which is called apt, right? You can look up the details of apt online. For our purposes, we just want first to update the local repositories, list of repositories. And after that, we say, okay, anything that needed an update, go ahead and update those, bring in the new packages, and, update those packages. So right now it's doing that. And the last line here is the one that matters to us the most. And let me kind of, pull up my marker. So what we need here is certain tools that are required to be able to compile the code. That is part of the package called build essential. Then while we are building our source code, we also need the header files that relate to the current version of the Linux kernel that we have, right? And the way we get these headers is we say, hey, install the Linux headers. And this right here is a dynamic command which fills in the version number. And what version number this is? This is the version number of our kernel, right? And then kmod is another utility that deals with, loading kernel modules and things of that nature. So all in all, we only need these three utilities, or headers and two utilities to be able to compile our code. So let me first, you know, go ahead and show you what version of uh, Linux kernel we are using, and the command is uname -r, and then the version is 6.8.0-35 generic, and this entire text gets put here. So this is how it will look essentially, right? That is why we have this. All right, so let me copy all of this, paste it here, and let's go ahead. And in my case, everything was already installed, so there was nothing to install and nothing to upgrade. But in your case, this process might take a while. And now that we have all of this with us, we are ready to dive into Linux kernel driver development and run experiments and learn through that. So with this, I'll see you in the next one.
So let's talk about the Linux kernel and when it becomes relevant, right? And in an attempt to do that, what we'll do is we'll imagine that we have a very simple system. So the system has a CPU, it has a DRAM, right? So this is all of this is DRAM, and then it, let's say, has a ROM, right? And then let's say it has the SSD, right? So let's briefly talk about what the Linux kernel is, right? What is the kernel? What should you imagine when we talk about kernel? So we'll keep the model very simple. We'll keep, we'll ignore a lot of details and focus on like the fundamental things. So a kernel essentially provides us with a scheduler, and a scheduler manages processes. And the other thing that the kernel does for us is it allows us to manage hardware, right? So it allows us to manage hardware. And let's take a look at this part now. So let's say you have a machine, right? Let's say you have your workstation, laptop, something like that. And to that, let's say you have connected a camera, right? And so what we now want to do is connect this camera over the USB and then fetch frames from within that camera, right? And this camera can be of any company, right? It can be from X, Y, Z, so on and so forth. And it would be fair to imagine that if you have the kernel running here, the kernel needs to know about what kind of camera this is. And once it knows about what kind of camera it is, it also needs to have some code that helps it manage this camera. My claim at this point is that that code which helps it manage this camera is called the driver. Right. We'll speak about this a lot more later in other videos, but this is the notion of driver. So we are going to manage hardware using kernel drivers, right? And so somebody needs to load it in and so on and so forth. That we are going to take a look as part of this series. But this camera, hopefully you're convinced that there is a USB port here, and then we need some code that can manage the USB port, and that's another kernel infrastructure, or again driver, right? So something like that. All right, so this kernel then is essentially, we can think of it as it manages processes and it helps manage the hardware, right? Okay, so question then is, where is the kernel stored? So the answer to that is that the kernel is stored, let's say, as an image in the SSD. So, well, it's not really an image. It can be a bunch of files and so on and so forth. So essentially, a bunch of files, and that's the kernel saved in the SSD. That is important. Then the question is, but the executable code must come to DRAM. So the kernel needs to be loaded to the DRAM, and from the DRAM, the CPU will execute stuff. Okay. And then there is ROM, and ROM is also connected, or like the CPU can reach out to ROM, and obviously CPU can reach out to the SSD. The question now we are wanting to explore is, at what point does the Linux kernel come from here to here? So let's talk about what happens after power on. So we turn the power on, and a bunch of things happen, and let's say the CPU is powered on. So the CPU essentially, what it'll do is it'll go to the ROM, fetch the code from there, and start to execute. And what kind of code is available here? The code that is specific to that system, which the system maker has provided. The system maker can be Intel, can be Lenovo, it can be AMD, so on and so forth. Whoever creates that motherboard kind of a thing is the one that will they that who are supposed to know how this CPU is supposed to kind of boot up and proceed. So one of the things that the ROM code has is turning other things on, right? And remember, the DRAM needs to be turned on for the Linux kernel to be copied here, right? And again, go back and remember what the Linux kernel does. It's just for management of processes, and it handles devices, or it helps us manage hardware. But this functionality is very generic, right? And something like which hardware to turn on, when to turn it on during the boot, that the Linux kernel will not know. It's an abstraction. Think of Linux kernel as an API that can do addition, right? So the thing that can do addition, you need to first of pass it x and y. That's one thing, but the value of x and y needs to be decided by somebody else, right? So the Linux kernel can do scheduling and management of hardware. It can help you with that, but someone needs to turn on the basic hardware that the kernel can sit on, right, or operate out of. So that's DRAM. So who will turn on the DRAM? Well, some part of ROM or later stages of the boot. So you must have noticed that when the system turns on, it kind of, well, before the screen comes up, it kind of goes ahead and checks if a RAM is available, if the timer is available, so on and so forth. And if something goes wrong, you see a message on the screen saying, hey, there is no RAM, cannot boot further, bye bye, right? So all of that kind of checks are coming from here, and the ROM code cannot be modified. That is why this has like very bare minimum stuff that is absolutely necessary for any system to boot. Now, once this happens towards the end of the ROM code, like as the ROM code's execution comes to an end, what the ROM code will do is instruct the CPU to copy some other code into the DRAM. And I should also mention that the ROM code is involved somewhere in ensuring that the DRAM is turned on. Right? So the DRAM is active by the time the ROM code is exiting, or the frequencies are set correctly, and so on and so forth. So DRAM is active, ROM code is exiting. So the ROM code will fetch some more code, put it in the DRAM, and then the CPU will execute that code. And that code, what it does is it kind of prepares more hardware. Maybe it provides user with certain security configurations during the boot up, the BIOS settings or the UEFI or U-boot environment that you guys would have seen. That is coming from this intermediate code, so to speak. So this code is essentially then offering user to select between OSs and things of that nature. All right. And now what happens is this code, as it is completing its execution, as it is coming towards like an end, it will copy over the Linux kernel somewhere in the memory, right? Uh, Kernel. And then what it will do is it will ask the CPU to go execute that kernel. It's like, hey, whatever the kernel requires, minimal hardware that I have enabled, you can now go ahead and execute the kernel. I've copied it in the RAM for you, right? Okay. So now we also talked about that the kernel can handle certain hardware, right? It can help us manage hardware. Now what happens is the kernel internally has lot of drivers, right? Which the machine makers like Lenovo, if it has a Lenovo camera on the laptop, so these guys will ship or rather take their drivers and submit it to open source as part of the Linux kernel. So whenever you're booting up the Linux kernel kind of has the driver for that particular camera already. In most cases it does. If it doesn't have, we have to add the drivers much later. That piece of hardware wouldn't be functional until that hardware is manually added much later. But right now let's talk about the drivers that are already present. So let's say something like the USB driver will already be present, right? So now the idea then is the Linux kernel got the control, but it needs to know where the hardware is. In fact, what all hardware does your system have? Right. And let's now add in more hardware here. Let's say we have two USB ports. So someone needs to tell Linux kernel information about what all hardware is available, which is the make, what is the hardware, what driver to use for it, some hint related to that is required. And now comes the concept of something called DTB, which is called the device tree blob, right? So this is a data structure. Uh, hmm, This is a data structure, and this data structure in a tree-like fashion describes who is connected to whom, what all at what all hardware is available, at what memory address is it available, so on and so forth. So remember the intermediate code, the UEFI or the BIOS code that we were talking about. So that code also passes some other information, and there is like in SSD we'll have something else which is called the DTP, and that DTP is also passed to the Linux kernel by this software here, the intermediate code here. And this intermediate code, by the way, is called bootloader, right? So it is helping in the boot stages, prepare the machine for the OS. And so the bootloader essentially passes, so bootloader passes, the kernel, the DTB. And how does it pass? So it simply says, hey, CPU, I'm going to go now. My time has come. But remember to fetch the code from this X address in the memory. That's where I have put the Linux kernel for you. And oh, by the way, also save this information about Y. And if the Linux kernel needs it, it'll come and look. And where is this Y information stored? It's stored within a few of the registers or one of the registers, let's say R1 of the CPU. So CPU has some internal registers which it uses for bookkeeping. So one of the registers, or 64-bit worth of memory, that kind of stores the address of where the DTB is loaded. So you can now imagine that as we turn the laptop on, the boot code or the boot ROM code is executed first. Certain basic checks are done. RAM is present or not, XYZ power supply is enough or not, so on and so forth. Once those checks are done, the boot ROM copies over the bootloader, right? Copies over this bootloader and puts it in the DRAM. And DRAM is also activated by the boot ROM. So the DRAM is ready. The bootloader is loaded there. The bootloader goes about turning a lot of things, on, collecting some initialization information, and then it composes or copies over this DTB, puts it in the location in DRAM, copies over the Linux kernel, puts it in the DRAM, and before it exits, it passes CPU that information. It sets, so to speak, the program counter to the Linux kernel address, and it loads one of its internal registers with the information about where the DTB is. And once the DTB information is available and the Linux kernel starts to boot, the Linux kernel reads the DTB and figures out, okay, which USB port, who is the maker of it, what is the driver, do I have the driver? If I have it, run it, right? So that's how we have the Linux kernel booting up. And if it has the device drivers, it will use those. If not, it needs to be manually loaded. And as part of this journey, part of this series here, we are going to focus on how to write a device driver and assume that you're writing it for a hardware that is right now not released in the market. So you're writing that device driver, submitting it to the Linux source, and while it is submitted to the Linux source, the hardware is released to the public. So as the public, gets a new laptop, downloads the Linux kernel and installs and runs it, the driver is already available and the hardware just works, right? So that is the idea. And one thing that I want you to remember about Linux kernel as a mental model is the Linux kernel is simply doing process scheduling, and it's also doing hardware management. And the drivers part typically comes when we are talking about hardware management. And before we go, remember I mentioned that the Linux kernel is like the add API, for example, which adds to number x and y. You can imagine, instead of maybe x and y, it's just, let's say, y, and it simply adds y plus 1 and returns back. So this y you can think of as the DTB. It's a parameter to the Linux kernel that it needs to be able to understand what all hardware is available, right? So with this, we kind of have the imagination and the mental models that we need in terms of reason about device drivers and start to develop the code. So with this, I'll see you in the next one. So there are a few more things about the Linux kernel that I would like us to remember or be able to imagine as we move forward in this series. So, okay, first things first, let me get myself up here. All right, so we were talking about, things that we need to remember or we should know about the Linux kernel. So first off, the Linux kernel, I'll just write it as kernel here. It kind of operates in a privileged mode. What does privileged mode mean? It means that the Linux kernel and obviously the kernel here has drivers as part of it, so the kernel can reach out to the hardware, right? And this is important because, well, the Linux kernel is kind of one of the features is that it helps us manage the hardware. But the question is, why can't a user application manage the hardware directly? Well, the answer to that is we would not like the application to kind of take full control of the hardware. Then it can do whatever it wants. That is number one. And we would want to restrict it. We would not want it to do whatever it wants with the hardware whenever it wants to do, we wouldn't want that. And the second thing is we would like multiple applications to share a hardware. For example, let's say we have the solid state drive. The state drive has, let's say, some partition on it, and partition has various files on it. And then there are different applications that are wanting to access different files. So all of them are essentially now wanting to access the SSD as a hardware. So we wouldn't want one application to own the SSD or have like a lock on it or mess around and use it in whichever fashion it wants. We would want somebody to provide like a very nice, serialized and managed access to it. So that's one of the reasons the kernel running in the privileged mode has access to the hardware. And as you can guess, the applications run in unprivileged mode, right? So that then means that the application needs to talk to the driver, right? And application somehow needs to convey its intentions that, hey, I want to read this camera, and can you, copy over the buffer, the video buffer, or the frame, so to speak, to me, right? Can you give me that frame that's available in the camera? So the user application here needs to talk to the driver to do any interaction with the hardware. Now, around this point, I want to kind of just present a case for how CPUs are, and that will add like more clarity. So CPU, for example, the ARM A V8, based on the V8 architecture, the ARM A class of CPUs, the 64-bit one, and we also have like a free course on this, and that you can check and learn more about these CPUs. So the ARM A CPUs has something called execution levels, and the execution, or sorry, not execution, exception levels. And the exception levels are like EL1, EL0, EL1, EL2, and EL3. Now, the Linux kernel in this case runs in EL1, right? And as you can imagine, as part of the execution level one, the hardware, the CPU is designed in ways that it can access different features of the CPU. For example, the status, like it was the addition a positive number, did the subtraction lead to like a negative overflow, did it or did the addition lead to like a overflow, did the subtraction lead to a zero, so on and so forth. Those kind of details are kind of captured in something called status registers. And the EL1 then, or the software executing in EL1 has access to those kind of things. And the kernel then runs here. The user applications run in exception level 0, in which case, as you can imagine, the hardware, when it's running in exception level 0, it turns off certain features. And so code running here cannot access such CPU status registers. I gave you an example of a status register. Some of them, EL0 code can access. CPU configuration registers, for example, the EL0 cannot access. So now you can imagine the kernel is running here, the user code is running here. And so any access to the hardware that needs to be done, the control needs to be passed from user space, so to speak, which is this, right, from the user space down to the kernel space. And now here's another interesting thing that we need to know, which is from the user space to the kernel space, the control is passed, or the requests are made via something called system calls, right? So system calls is how we essentially, from the user space, ask the kernel space to do something for the user application, right? So let's say we are wanting to do like a thumbprint verification or thumbprint based authentication. The user space will essentially ask the kernel space to kind of go, do something about the authentication process and just pass yes or no, one or zero as the answer. So the user space app never accesses the thumbprint sensor, the fingerprint sensor, but the kernel does something around it, right? All right. And how does it do it, or what is the way to request from user space to kernel space? It's system calls. And what are system calls? So system calls are essentially a bunch of actions. These are bunch of actions that over the years people have realized, the developers have, or rather the maintainers of the Linux kernel, the Linux kernel development community, have realized are common or generic. So for example, we would want to perform read on, let's say, the camera buffer, and we might want to perform a write operation on the display buffer. Load data into the display buffer, read data out of the camera buffer. So read and write, for example, are such generic operations that we would want to perform on different hardware. So the system calls are those. So somewhere then, what we can imagine now is that the Linux kernel, the drivers within that, right, are somewhere supposed to implement the system calls, right? Somewhere they are supposed to, like, when let's say we were asking, hey, can you read the image buffer of the camera, then we are essentially saying, hey driver, who is handling the camera, can you go and read that buffer for us, right? And so somewhere the device drivers, and this is key, by the way, this is like a very important point. So the device drivers somewhere implement somewhere implement system calls, right? And we'll take a look at these in details as we develop the code. But this background information is an absolute necessary one for you. User space is something that you should remember. Kernel space is something that you should remember. Privileged, non-privileged, and the communication between these two happen via system calls. And we'll take a look at the system calls in detail as we write our drivers. And we also mentioned that the kernel has drivers and the drivers implement the system calls, right? So with this as the background, now let's take a look at how does the Linux kernel uh, house or hold the drivers within it. So let's call this D1, D2, D3, D4, and D5. And this is our kernel. So the idea is after boot up, if the kernel, whatever drivers it has, if it is using those, then we call them as boot time drivers. This is not a specific, like, this is not a standard keyword. I'm just coining a term here. Boot time drivers, or you can also say, like, built in drivers. This is like more accurate, honestly, right? The second one, built-in drivers. And let's say if you have a piece of hardware like a camera system you're working on, or some new fancy device that your team is working on. So the driver for that won't be available in the Linux kernel community or in the Linux kernel source. So usually what happens is the developers, they will develop that driver and push it to the kernel mainline, right? They'll push it to the mainline, and then they'll kind of download and create like a new kernel image, right? New, recompile the kernel. But when they're developing it, one of the ways that they can check whether their driver is working correctly or not is by injecting it or loading it into the live system, right? So you have Linux kernel running, you're writing a driver, you want to test it out, you connect the hardware. Well, right now the Linux kernel doesn't have any driver. You're writing that driver, because of that it doesn't have. Now, what you want to do is compile your driver and be like, okay, can I load it into the live system so that I can check whether my driver can handle that interactions with the hardware correctly? So those are called the loadable kernel modules. Or you can also call them loadable kernel driver, right? And this is something that we are going to focus on as part of this course. But now when you're essentially developing this Linux kernel loadable module, the idea is that the Linux kernel provides you with a way, or provides all of us with a way, to be able to load that in. And what does loading mean? And what does it mean that a driver is loaded and activated? You can imagine that the kernel allows us a way to specify how to absorb the driver into a live system, and then it kind of activates and initializes. And that is for later. As we dive into the code, we'll talk about how it loads and things of those nature. But one other thing I want you to imagine is the idea of constructor and destructor. I might have got the spelling wrong here, but the idea of constructor is when you initialize a class, so to speak, you execute, some initialization code, and as that object goes out of scope, we call like the destructor, and deinitialize or clean up the kind of memory that the object acquired, and so on and so forth. So this is coming from the object oriented programming world, but somewhere the Linux kernel provides some feature that is equivalent to constructor and destructor, and that's how, like, as we submit our module, loadable module, the initialization sequence is called which can, essentially establish some handshaking or initialization of some state machine that is required in managing the hardware. And as we remove that module out of the kernel, it will call the cleanup or the destructor sequence. We'll dive into this a little more, as we go along. Actually, a lot more as we go along. But for now, I just want you to remember privileged, non privileged, user space cannot talk to the hardware directly, must go through the kernel via a device driver. And the way user space talks to the kernel space is via the system calls, and the device drivers implement the system calls, and then there is this notion of constructor and destructor. So if you're clear with all of this so far, if you're convinced with this, in the next one we'll dive into writing the kernel module. We should discuss about the system calls a little more before we are ready to write the code. And so this one would be like the last video on theory, and then we dive into the code. In fact, even in this one, we'll take a look at some code, although we won't write the code. All right. So we were talking about system calls, and this was a way for user space uh, to kind of talk to the kernel space. And in the kernel space, then I mentioned that there are drivers, and the drivers would need to implement these system calls. Now, what I want to specify very specifically is that the drivers typically implement two types of system calls. Like the kernel also has like other code, the infra and the process management related code and all of that, which also implements a lot of or not implements, but it's dependent on a lot of system calls, right? So there are some system calls, for example, fork, that can take the current process and create like a replica of that process, and that's process management related system call. But then the device drivers implement system calls which relate to file operations. So we talked about read and write, for example. So those system calls, for example, are file operations related. And again, what is the link between file operations and a device? We'll come to that. Like, what is the different or relation between hardware and file operations? The other thing is they kind of implement hardware management um, related system calls, for example, the IOCTL or input output control, also called ioctls, right? All right, so now let's spend some time on this, and then we are good to go and write our first driver. So turns out that Linux uh, uh, typically treats everything as if it is a file, right? As if it is A slash B slash C. So everything in Linux is a file, and then on a file you can perform certain operations, like opening the file, closing the file, reading the file, writing the file, seeking into the file, so on and so forth. So it turns out all of the interactions that you might want to do with the hardware also kind of fit this notion of open the hardware, read some content from the hardware, write into that hardware if required, and then kind of if depending on what kind of hardware it is, you can also do some sort of a seeking, and then we just close that hardware. So pretty much that's all. So what Linux does is Linux will map a hardware, it'll expose it as if it was a file, right? And if it exposes it as if it was a file, then we can do file operations on it. And so as you can now imagine, the drivers are going to implement what to do when the hardware is being opened, what to do when the hardware is being read, what to do when the hardware is to be written to, right? So all of those functionalities will be will the driver will need to implement those as these file operations related system calls, right? So that is one thing. And now the other thing is that drivers can be of majorly three types. One is called the character driver, the other one is called the block driver, and the third one is called the network driver. Right. So we are specifically going to take a look at character driver, because once we know how to write these, the character drivers, it becomes easy to write the block and the network drivers. Now, what kind of drivers, are within the category of block? Well, file system related, or rather, drive related, your hard disk and solid state drive, storage related, more appropriately. Right. So storage related drivers are block drivers, for example. Then network drivers are the drivers that deal with Ethernet and so on. But we are going to look at the character drivers, and somewhere we are saying that a driver or device is exposed as a file. Right. So the interface for the user space to request the call to the kernel space is to do some operation on a file. Right. So let's say, for example, we have, okay, let's take an easy example. Let's say we have a UART, right? A UART is universal asynchronous receive transmit module. You can send like a byte at a time to other computer and so on and so forth. Uh, Pretty old protocol, but still actively used. So let's say this UART is reachable, or the driver handling this UART responds to reads and write onto the file called TTYACM0, for example, right? So as the user code or user application attempts to read this file, the read on this usually triggers the read system call implemented by the device driver for UART. And within this, then, what will happen within this, it will have the functionality to go read some information from the UART and then pass it back to the user code. Right? So, this is how we go from user code to kernel code or kernel driver via system calls, and the system calls are triggered by doing read and write, or by doing some operation on the files, right? So this is also very, very key, that a device driver is triggered by doing file operations on a file, and that file is kind of representing access to that hardware, right? And now let me just quickly we'll get rid of this. And what we have here on the screen is a file from the Linux kernel, which is the fs.h. And actually, let me go ahead and zoom this in. Right. So, oh wow, okay, zoomed a little too much. And let me go down here. Right. So this file is called the fs.h, and then on line number 1999 we see these file operations, and within that we have the seek, the read, write, iterative something, read, iterative write, then some polling, some poll here, so on and so forth. There's open here, there is release here, which is same as, I think, same as close, and there is flush, so on and so forth. And all of these are operations that we can do on a file. Right. And as we'll see forward, the file operations is something that we'll need to kind of implement while writing a driver. Right. So again, the takeaway from this video should be that user space talks to kernel space using system calls, and the device drivers implement majorly two types of system calls: one that relate to file operations, and the other that relate to hardware access, which is, or hardware management, which is IO control or IOCTL, right? All right, so with this, we pretty much have the imagination and the background we require to be able to dive into writing a loadable kernel module. And in the next section, we'll start with our first loadable module. Okay, so now we are going to write our first device driver module. And to be able to do that, we have some prerequisites or preconditions. And that is that your multipass instance should be running and VS Code should be connected to it. Now, to what I have on my screen here is a terminal screen, and then in the background there is VS Code. And I'll just quickly show how you can go about starting the instance and connecting to it. So my primary instance here, the virtual machine is stopped. It's not running. So first I have to get that running. So I'll do multi-pass start primary. It should take few seconds to start. Let's just give it few seconds. Well, it's actually taking longer than I anticipated. So, yes. Okay, perfect. So now, if we do multipass list again, we should see that primary is in running state and it has got an associated IP address. Now, recall that we had used this IP address in VS Code. By the way, we do not need this terminal anymore, so we'll put it in the background. So we'll come to VS Code, and under this remote explorer, notice that previously we had connected to primary and the IP address was exactly this. In your case, the IP address might vary, so that's fine. But we want to connect to the LDD directory. So I'll just go ahead and click on this arrow here, which says connect in the current window. And once it is trying to connect, it asks me for password. The password was P. That is the password I had set. You could have set something else. And also, if you don't readily see this terminal, what you can do is go to the menu, go to terminal and click on new terminal. So we have new terminal here. Let's just pull it down here somewhere. No. Okay, let me again do that. Uh, Orange new terminal. That's fine. We'll work with this. So right now we have no files here. And also at the bottom it says SSH 192.168.64.12, which is the IP address of our machine, the primary machine. So we're all good now. Okay, so now what we are going to do is write our first module and just kind of print hello world, and then we'll kind of tease apart all the parts that were involved in compiling it, why was it written the way it was written, and also what the make file does for us. Okay, so we need two files. I'm going to call the first one ldd.c because Linux kernel modules are written in C. Lately there has been support for Rust also, but we will write the modules in C. All right. So the first file we created was ldd.c. The second file we want to create is makefile, and please ensure that the file starts with an uppercase M, not a lowercase m, not like this. It has to be exactly this. Right. All right. So we have these two files and we have our terminal. Let me put our terminal on the side here. Perfect. So within the C file now, let me just cheat and copy paste, some bits here. All right. So I have approximately copy pasted, 18 lines worth of code here, right? 18 code lines. And we will come to what these lines mean in a while, in a bit. And let's go ahead and save this. And then let's go and populate the make file. So in the make file, let me also cheat again and copy paste. So I've copy pasted about 7 lines here. Let me, no, just a moment. Um, Let me reduce. Yes. Okay. So now coming back to the ldd.c. So our intention is that we are wanting to write a kernel module that can be loaded into live kernel, right? And my claim is that the 18 lines here are good enough for a hello world program. And uh, this piece of code here goes on to explaining or we'll kind of take a look later once we have tried the experiment, that this goes on to explaining the idea of what I was previously referring to as constructor and destructor. So what you see on screen, the code is for constructor and destructor, and what this is and why this is useful, that will come to also. But just kind of for now, take it on faith, or just trust me that this is the bare minimum to be able to write a module that the kernel can accept. And okay, then let's go ahead and uh, talk about these two files. So we have the module related code here, and we have the compilation code here. So we would want to compile the code to become a kernel module, and that uh, is done using the make file here. Now, for those of you who do not know what make files are, well, these are just a way to automate, right? And we'll talk a lot about these in a while, but just for time being, know that makefile is for automation. It helps us run commands, like bunch of commands automatically. And then the ldd.c is where our kernel module source code is. All right, perfect. So if you're able to follow through this much, let's just go ahead and kind of compile the code. So I'll just in our terminal go ahead and do make, and if you see, it went ahead and printed a lot of messages, did something, and also it has created like tons and tons of files here, right? Okay, watch this again. So if I do make clean, it will kind of wipe out all the extra files it had created. uh, so right now, then on your screen you only see the two files that we had created. But if I do make again, notice that it has created like bunch of files, and of these files, of all the files that it generated, the ldd.ko is what is of use to us. That's the actual kernel object or kernel module, right? And so far, this is what we have done. We started off with a .c file, and this is where our source code was. Then we kind of compiled it and created a ko. The claim is this is the kernel module. And the next step that we want to perform here is to inject this kernel module into the kernel. And then after that, verify. Verify in the sense whether or not kernel accepted it, right? Okay. So uh, then the way we do that is we call a utility called insmod, and insmod is the utility that will take your kernel module and inject it into the kernel. So let me then uh, submit, or provide it with the name of the module, and it has to end in a .ko because it needs to know name of that object file. All right, so sudo insmod ldd.ko. Things seem to have gone well. If I do echo dollar question mark, that essentially prints the status of the previous execution, and 0 means a success. So this command here was a success. So the next thing we want to do is verify that our kernel module was injected and accepted by the kernel. So my claim now is we had two functions here, which again we'll come back to in a while, but there was a print statement here and a print statement here. My claim is this is the print statement we should see, but see where. So what we are instructing the kernel at this point is do a print somewhere of this statement, and that somewhere happens to be the kernel log buffer. So we now need to somehow go and print this log buffer somewhere here, so that we can see whether or not this was printed. Right. So the kernel internally in the memory is maintaining a log buffer, and it continues to print there. And what we instructed using this print k function here was to print this in the buffer, right? And that will be one of the hints in which case we can confirm that our module was loaded. So then the question is, how do we go about printing that buffer? And the way to do that is we type sudo and and execute the utility dmessage. Dmessage essentially will print the kernel messages for us, the kernel buffer. All right, and so we have a lot of things printed here, and at the end of it, we do see, hello world from in pajama, and that is same statement as here. All right. And then we also see corresponding to LDD colon, LDD is name of our module. So it is printing something else. It's like loading out of tree module, taints kernel, module verification failed, signature, blah, blah, blah. This will fix later on. But the important part is that the kernel accepted our module and it went ahead and executed this function. And why this function, that also will talk about in a minute. So now the module is in the kernel, and let's say we want to plug it out. So how do we kind of uninstall or remove the module? So for that we have sudo rmmod and ldd. So we just have to give the name of the module. We don't have to give the .ko this time. If we give .ko, that is also fine, but that is not required, strictly speaking. All right, so sudo rmmod ldd, and now we go ahead and print the d messages again. And now um, if you see this message is what we have printed, right? So what the kernel has printed. So somewhere then it should ring a bell around the fact that whenever we insert the kernel, this kernel module into the kernel, whenever we insert it, this function was called, and then whenever we kind of remove the module, this function was called. And then somewhere this kind of relates to the idea of constructor and destructor. Right. And we'll talk a lot about this in a minute, but all of this here is just kind of some header files, some macros. Similarly, at the end here, these are some C macros, and these are the only two C functions that we have written. Right. And now let's go ahead and talk about which file means what and what things mean what. So okay, let's get this on the side, or actually let me just put it here. Let's go here. All right, so what part of the code is doing what? Okay, so the kernel requires that each module have in it a function, right? A function that the kernel can execute once the module is injected into the kernel. Right. And so that we call the init function, or referred to as the init function. So again, the idea here is that when the module is inserted, this is the function that the kernel is going to call. And what does this function typically do? It's supposed to kind of set up some bookkeeping information, register or create a queue, something of that nature. Anything that the core functionality of the module will require: memory, queues, events, registering for events with some other modules, so on and so forth. That goes into the init function. Now, similarly, when the module is kind of taken out of the kernel, then it needs to execute some sort of a cleanup function or exit function or release function. I mean, these are the different names people refer to it by, right? Typically, common ones are cleanup and exit function. So similarly, there has to be then a function that the kernel can execute once we have instructed it to kind of remove this module. right? And what kind of functions or what kind of functionality does the cleanup function have? Well, it can do cleanup related tasks like freeing up the memory, unregistering for events, returning back the resources, gracefully shutting something down, and so on and so forth, right? Those kind of things are part of the exit or cleanup function. And now what you see here is we have this one function, right? It's an int type, returns an int, which is 0 here. So the idea is if something went wrong here, if it was not able to get the resources that it required, it should return like a negative number, some error code, and then the initialization or insertion of that module fails. That's the idea, right? So it will essentially you know return like an integer number, and then the name of this can be anything that we please. So there is nothing sacred about pajama underscore module underscore init. It could have been just as well xyz. That's completely all right. Then the function implements the body. In our case, we only printed a statement, right? Okay, so that was about one function that we wrote. The second function we wrote, well, it doesn't return anything because the cleanup, if it fails, the kernel is left in like a bad state. No, but and cleanup is also like the last thing to be done. So again, the name can be anything here. Nothing sacred about pajama underscore module underscore exit. Name can absolutely be anything. And the init function doesn't take any parameters, and so does the exit function, because there is kind of, well, at least known to me, there are no inputs passed to these. So the input type or the function parameters are nothing, so void. Okay, then there are two lines here which are very special, right? And if you see, the name that is used here must go here, and the name that is used here must go down here, right? Exit and init. So what are these? So essentially, the kernel needs to know what function it needs to call as part of initialization. It needs to have that function pointer, so to speak. And similarly, during exit or during like removing the module, it needs to know which function it needs to call to perform that exit. Where is that recipe, right? And so these are two macros, right? And what these macros do, we'll tease this apart in later videos, just so you understand all the details, internal details. But take it on faith right now that this is a way in which the compile, like during the compilation process in the .ko file, there are two symbols exported, right? The pajama module init and pajama module exit, right? These are two symbols that are exported, and while consuming that ko file, the kernel can identify, oh, okay, I'm supposed to go after this function when I'm trying to inject this module, right? Or insert this module or consume this module. I'm supposed to go after this function. And similarly, when exiting, I'm supposed to go after this function. So these two function call like thingy here. Let me clear the screen now. So these two function call like thingy are actually C macros, right? And that is why they can be called from outside of a function. Otherwise, a function call requires that you call it from within another function. These are lowercase function like looking, but they are not function calls. And also, I think I should go ahead and change the theme a little bit here, because it's not uh, very evident. uh, Let me choose a familiar theme. Maybe I'll choose this. So the other thing I want you to notice is that there are semicolons here, which in my previous theme wasn't visible. But rest assured that there are semicolons. But these two, again, are macros. These are macros, and so are these. So these macros up here, by the way, also I should mention that these two macros at the bottom line, 17 and 18, come from these header files. These header files are required, and these header files are required for these macros and these macros. Okay, and then what are these macros doing here? So these macros are essentially helping us specify the license that this kernel module is going to be released under or is available under. And there are like various licenses, but we are using GPL. Okay, why this is important, and this is mandatory. If we don't have this, the kernel will not accept this module. I can go ahead and do like a demo of that in a bit, but this is mandatory, right? And okay, why is it so? The kernel then has modules internal to it, various features, and those features might be in, like, let's say MIT license, GPL, Apache 2, so on and so forth. Now, the thing about the GPL license or the licensing terms is, if you are using a permissive license, you will be allowed to use the feature from other permissive license, right? And then there is like a hierarchy of which license allows you to use which other license and so on and so forth. But the idea is, if let's say we use like a restrictive license here, then the functionality from the other permissive license will not be available to us. So if you don't plan on releasing if you don't plan on releasing your source code to the public, let's say, under the GPL license, then you're not allowed to use other functionality that's available as part of the GPL license, which is marked as GPL in the kernel. So then specifying which license you're using becomes absolutely important, so that the kernel can allow you to access resources or functionality that are released under certain licenses. And you can search and look up in terms of, like, which licenses, like writing a module in which license allows you access to which other functionality in which other license, right? All of that is available on the internet. Then these two macros here are optional. If I did not put them, that would be all right. But what's happening here is, I'm just saying that, hey, the author of this module happens to be, having this name here, and then I'm describing what this module does as one liner, right? That's about it. So what happens here is, people can understand some description, or the kernel can record and print some description, so that other developers can understand what your module is doing, and also they can reach out to you in case something goes wrong or something needs to be improved. So these two macros are essentially for that. Now, with this, let's first quickly try out an experiment wherein we do not provide this line. And also, let's get rid of, actually, first, let's get rid of these lines and let's have this. Let me then pull up the terminal. Then we do like a make. Okay, so the module is built. Now we do sudo insmod uh, ldd.ko, and then we do sudo the message, right? And at the end here, we again have hello world from in pajama. And also notice that the kernel did not uh, complain about anything. So now we'll go ahead and do sudo rmmod ldd.ko. Again, the ko is not important when removing, but we'll just go ahead and try that, right? And if you see, again, the module is removed. Now, allow me to introduce another command here, which is sudo dmessage, actually an option to the command. So sudo dmessage printed the kernel log. And what we're going to do now is say use -c option. And what that does is prints the kernel log and also clears it. So next time we do dmessage, it'll print nothing, because that buffer is completely clean now. All the logs are printed and the buffer is clear. And this will be helpful when we specifically want to see prints from our module. And let's say if your kernel is very noisy, then it keeps on printing stuff, and then somewhere in between that you will have your prints. To get rid of that kind of searching between the noise, we can clear the kernel buffer. All right, so now let's go and comment this line out here, the fourth one, the module license, and then try and do make clean to clear everything out, then do make again. So we built our kernel, and as you saw, or as you see, not saw, but as you see here, it the compilation process itself fails and says, hey, I see a missing module underscore license, so it cannot compile further. So the kernel, or rather the build process, enforces that we state uh, and a license, and once I specify the license, the compilation goes through. Now when I'm going to do, let's say, ins mod and then do dmessage, you'll see that there is only one line, and this was because we used dmessage minus c. I'll go ahead and do mod. Oh, actually, before that, now if we were to do mod info, or info mod, I think, um, info mod ldd.ko. Okay, let me find out the command real quick from my cheat sheet. Okay, so it is mod info. So mod info ldd.ko. So if you see, it kind of uh, prints descriptions, right? And then there is it prints the license, it prints like the name, what path it is available at. This is some, source version, something, the name of the module, and some version magic, right? Now, what I'm going to do is enable these two lines. Let's go ahead and also remove our module. Remove the module. Let's do dmessage. Yeah, so we also see the goodbye message here, which is perfect. Now we clear the logs. So now when we do sudo dmessage, nothing's there, which is perfect. Now we'll do make clean, do make, and then we go after mod info. Notice for using mod info, we don't have to have the module inserted. It's just that we need to have access to the KO file. And once we have that, it'll go ahead and print information. And as you can see, it's printed the author's name here and also printed the description that we gave as part of this macro. So that then is a bare minimum code that we need to write a Linux kernel, a kernel module. And then in the make file here, this deserves like a video of its own, but I'll quickly explain what's happening here. So the kernel comes with its own build system, right? So this is like a complete set of tools, automation, all of that. And somewhere we are injecting or providing it with information through our make file. Right, we are providing it our make file, and then kind of triggering it to launch this build system, and as part of doing many things, build our KO. And many things, I mean, doing generating like all of these different files here, right? And what these files are, again, we'll come to those later. So this object minus m plus equals to ldd.o, essentially we are saying, hey, we want you to create an object which is called ldd.o, right? And as part of this, as part of creating this here, the kernel will end up creating this, which is of use to us. But then we are instructing it that, hey, go ahead and include in the list of modules that you're going to create, just append to that this one module, right? And then we have two targets here, all and clean, and by default make executes the target that is on the top. So if we do make all, that is same as executing this target here, if we do make clean, which we have done a couple of times, then it executes this command right here. And in that sense, and make files are a way to automate commands. All right, so what is happening here? So this make command internally calls another make command. It says, okay, change the directory to wherever the kernel's build tree is, right? And this here is dynamically filled in. Um, okay, I'll show you that in a while. This is dynamically filled in, but we say, hey, change the directory to this. Then, by the way, the modules are supposed to be output into the present working directory, which happens to be this directory, this directory right here, right? And then we are saying, hey, go ahead and create your modules, right? So our make internally calls another make, changes the execution or changes the working directory to this, which belongs to the kernel, then says that, hey, make sure that you put the output in the directory that the original make was launched from. And oh, by the way, you're supposed to create modules. Right. So this is what the make command is doing. And then, or rather, the simple make command that we launch internally launches another make, something, something modules. Right. And then the clean here is essentially saying, hey, again, go back to, change the working directory to this, ensure that the modules you're looking at are from the current working directory and execute the clean command. Right. So let me quickly show you the output of all of this. Right. So when we do let me do make clean first. So if you see, it executed this command. Let me actually get rid of this. Yeah. So it executed this command make hyphen c, which is similar to this or exactly matching. Then lib modules. So this right here uh, is make executing a command line command, getting the output of it and putting that output here. And the output for this command, the uname hyphen r command, happens to be 6.8.0-35 generic that you see here, slash build, right? And then in like m equals to, it has substituted the path for the LDD, which happens to be, so if I were to pwd here, which happens to be home/home/ubuntu/LDD, that is here, and then clean. And then as part of this, make has, the build system rather has gone ahead and cleaned up the source code, right? And so all the files that were generated here disappear. So now when I do make then, or make all, both are same. If I do make, then it'll go ahead again, change the working directory to the kernel's build directory, point the modules or output of the modules to /home/ubuntu/ldd and create or execute the command modules. Then it goes ahead and does a lot of things. And then as you can see here, it's generating different files, right? So this then, 7 lines worth of automation here and 18 lines worth of code here are the basic essentials to even get started with being able to write a kernel module. And in the next videos, then what we'll do is explore all the utilities that we used, dive into like little bit details of the kernel and how it operates, and then from there we'll go towards writing or adding more functionality to our module. I'll see you in the next one. So one of the things that's used very extensively in Linux kernel modules or the development of it are the make files, right? Of course, there are many other ways in which people go about building their modules, but makefile is, well, I would say at the heart of it all. So we're going to take a look at the makefile and some, basics that you should be aware of, right? These are like good to know because they come up like again and again, and they're also kind of useful in terms of debugging the makefile or debugging your own modules build flow. So then, let me pull up the whiteboard here, and we are going to take a look at, as part of this video or this lecture, make and makefile, right? And what are like the link between these. right? So first off, make itself, like all lowercase make, is a utility. And what does this utility help us with? It helps us with automation, right? And automation of what? Automation of kind of, executing, commands, right? Commands of what nature? Everything that we can, write on the shell, so those commands can be automated. So anything that we were going to execute on the shell, on the terminal, that the make can do it for us. So for example, if you're aware of how we go about compiling a C file, then we say, hey, GCC, take our file main.c and then output it. Okay, just a moment. So we say then output it as, let's say, main. Right. And so this command usually we type on the terminal. So the idea then is we can have make execute this command for us. Right. So that's what I meant when I said that the commands we can execute on the terminal, we can also execute them using make. Now, where does make become useful? So when you have like lots of these commands to be typed like one after the other, let's say 5 or 10 of those, then each time doing that manually, typing, the 5 commands or 6 commands, become tedious, repetitive, boring, and it's subject to human errors also. So to avoid all of that, we can create like a recipe, and then ask make to execute that recipe, execute these commands for us, right? And then the question is, how do we kind of specify those recipe, and that's where the concept of make file comes in, right? And in this make file, this M here, the first letter in the, or first alphabet in the name, has to be uppercase. Right? So the idea then is whenever we execute make followed by something, and what this something is will come to in a while, but let's say we execute make, the make utility goes searching for exactly this file, and it'll open up this file and process the data given inside of it, and then kind of infer what commands to execute, and then go ahead and execute those, right? So that's that then. Make is a utility for automation, followed by something, and this something, by the way, is called target, right? And so make will go looking for information about this target in the make file with an uppercase M. Now, of course, you can have any name to the file and then end it with .mk, and then the idea is that we have to, while calling make file, tell it that, hey, the file that we are wanting or you to use in terms of searching the details of the recipes, we are specifying it with the -f option followed by the name of the file and then the target, right? And what target is, we'll come to that in a minute, but then execute the target. And so now make will not search for this make file, but it will go looking for this file name. And as soon as it finds this file name, it will open it up and look for information about how to execute this target, right? And okay, so if this much is clear, then we can come back to how this .mk or make file are written, how are these authored, what are the syntax and the rules. So the first thing is it can have many targets, right? A target is essentially, you can think of it as a short name for a complete set of commands, right? So the usual format is we have to specify the target followed by a colon, and then we can specify dependencies rather, right? So for example, here the GCC command depends on the existence of main.c. So in dependencies we can mention main.c. Now all the dependencies go on the first line then, and the recipes or the commands to be executed start from the next line. And then the idea is that there has to be a mandatory tab character here, and then we specify the command that needs to be executed. Right? And if there are multiple commands to be executed, they can go on new lines, each starting with a tab. Right? Each starting with a tab, and we'll see an example of this in a while, but that's the idea. And then you can have another target, and so on and so forth. The dependencies may or may not be there. For example, in our case, the clean command here, for example, and even the all doesn't have any dependency, right? Which is all right, because if you just want a target to be associated with bunch of commands, well, then that's that. Now the idea of dependency is that make is smart enough that if the dependencies have not changed, then it will not regenerate or re-execute the recipe. So for example, what I mean by this is, let's say um, x.c is used to generate x.o, for example, right? And then we have a target called xyz, and the target name can be anything. It just needs to start with an underscore or a alphabet, right? And you can play around with the names of the target, but the target, and then in this dependency we say, hey, it depends on a dot x, right? And as part of the recipe, then we say a tab character here, and then followed by gcc minus, oh, well, okay, let me do this here. So x dot c minus o, x dot o. Let's say this is our command. So for the first time that we call make xyz, and notice that this is the target. So it will go ahead, look at this and say, hey, it depends on xyz. Do I have xyz? Sorry, it depends on x.c. Do I have that file x.c? It's like, yes, I do. Fine. Okay. And now, uh, it'll then go ahead and execute this command. And actually, let me change this a little bit, because then it kind of makes a lot more sense. Let's say we want it to be output as xyz, right? Let's just call it this way. So when we are executing this target, it first says, hey, does the x.c exist? Yes, it exists. Also, is this file older than my output? First off, does the output exist at all? If it doesn't exist, then it knows that it must generate it, right? So the first time we execute this command, xyz will be generated, right? First time. The second time we just try again, then what make will say is, hey, I see that x.c exists, and so does xyz, and xyz looks newer than x.c. And if this is newer than x.c, then nothing in x.c seems to have changed. And if nothing changed in x.c, it doesn't go ahead and execute this. So that way make saves us effort also. It only updates what the dependencies of which are updated or changed. So now if we go ahead and make some change in x.c and run the make command, make xyz again, now it notices that, hey, this xyz file, yes, it exists, and it's older than x.c, which means this needs an update. So that is also another kind of benefit of using make and make files, which is it only compiles or regenerates the output files that are stale, so to speak, right? All right, so just reiterating, the format of makefile is target colon dependencies, then on the next line a tab character, and this tab is mandatory. It should not be 3 spaces, 4 spaces, 2 spaces, none of that. It has to be a tab character. And then you can have command 1 here, command 2 here. Okay, my spelling is messed up here. Command 2, and so on and so forth, right? So that's the idea of make, and make can It also has notions of variables and whatnot, right? Variables, functions, this and that. But this is the basic syntax. If you know this, you'll be able to make sense of what's going on, and what now or what might not be working. Okay, let me get this out of the way. And now if you look here, right, so this here is the all target that does not have any dependency, which is fine. Then we have a tab character here which cannot be seen, but trust me, it is tab. If I convert it into spaces, the make file won't work, the make utility won't work. Now this doesn't have any dependency, the name is clean, the target name is clean, and the command is right here. So what I'm going to now do, okay, one other thing I should have called out is when we execute make, when we simply call make, it will look for the make file with a like a uppercase M, and it will execute the first recipe available, right? It will execute the first target. If we specify the target, it will go after that, right? So that is the idea of make then. And what you see here at this point, this is essentially just a variable, right? So this right here, objm plus equals to essentially means amend. So objm will already be like, many things. And then we are saying, hey, add ldd.o at the end of it, right? And variables are like a different ball game, but just know that make also has this notion of variable, and it can, it can simplify life. Okay. So now what I'm going to do is just, for the sake of demonstration, I'm going to add ldd.c here. So all depends on ldd.c, and let's go ahead and execute make. So, make has executed the command, carried out all of these execution. Now note that we are not going to change anything in ldd.c, and so when I execute make again, it should somewhere say that the targets are updated. Okay, in this case it doesn't say, but what it doesn't say specifically, but what it is doing here is it has not executed or generated all of these output files, right? And let me then go ahead and maybe just put like a space here. So now ldd.c is modified, and once it's modified, you will see that it has again regenerated all the outputs as it was here. And also, if you notice, it would have generated only, okay, turns out everything was regenerated, not a problem. Perfect. So this is, so to speak, the dependency. And let's try out one more thing. So let's say, we are wanting to generate test.text, and it depends on test.c. And here's the tab character. If you see, it's a tab character right here. um, and then what I'm going to say is, hey, first off, cat the uh, test.text file, and then by the way, cat test.text again, and then after that, push it in, oh sorry, text.c, then push it into test.text, oh, right? And then after that, cat test.txt, right? So notice that there are three commands that it will execute on the terminal. Each one of them starts with a tab character. And what I'm going to now do is, first off, execute make clean, so everything is out of our way. And I'm now going to write test.c here, which simply has, I don't know, hello test, right? Let's say it only has this. I'm going to save this file. All right. So now if I do make test.text. So notice that this is the target, this is the dependency, and these are the commands. So what we should see here now is this, and this command getting executed. And this should again reconfirm to you that make is executing the three commands for us, which otherwise we would manually execute. Right. So let me go ahead and execute this. And if you see the first command it executed, was this, same as this. The output is available here. Then after that, it went ahead and executed this command, right? And then after that, it executed this command, the output of which is this. And we started off with test.c. We also now have the file test.txt. Now, as I mentioned earlier, if I try to execute this command again, it says, hey, I need not do anything because test.txt is already at its latest version because test.c did not change, right? And now I'll go ahead and um, uh, hello again. I'll just modify it. So now test.c is modified. So this is newer compared to this file. And so these commands should get executed again, right? So let me just go ahead and do that. And if you see, lo and behold, it kind of, executed these commands again. And obviously the content of test.txt, because of this line here, is same as the the content in test.c, right? So hopefully you're convinced that make is used for make is, oh, sorry, my bad. This has to be, yeah, lowercase. Make is used for automation, whatever the spelling is, automation. And then .mk is file extension if it's not named as make file. And make file, the m here has to be uppercase. This is the file that make by default goes looking for. And then within this file, or within this file, the .mk file, the recipe is target colon dependencies, on the next line, tab, and then commands, right? And before we leave now, what I'll do is I'll show you that if I convert this to spaces, let's say two spaces in this case, and execute the recipe again, uh, you know, make is complaining. We see make complaining, missing separator on line number 10, right? So it looks like things are good, but they're not. We should have a tab here, right? And the other thing I want to do is call this, something else. Let's say I call it piyush.mk. So now when I do this, he says, hey, okay, let me also remove test.text, right? When I try to do this, it says, hey, I found no rule, because it found no makefile, right? And now what I'm going to do is I'm going to pass it the -f piyush dot mk, and now all of a sudden it knows how to execute. So -f is the flag that we can pass a custom makefile that is not having the name makefile. If it is not named this, then this is how we pass it. So hopefully you're clear with what the make utility does and how the make files are to be used. This is kind of just FYI for young professionals. They kind of in the past have seen that people don't understand what make files are used for. So this lecture was specifically to call that out. Now let's do one thing, which is let's leave our environment, the way we had found it. And let me also go ahead. Okay, actually, let me remove and let me change this to make file, and we are good. So we are leaving our environment the way we found it. And with this, in the next lectures, let's explore the other utilities that we were using. Hey there. So as part of this video, we are going to explore a utility called lsmod, which is for list modules. And essentially, we are going to understand how it can be useful to us and what it does. This utility is kind of very handy when we are trying to, let's say, ensure or confirm whether or not our module is accepted by the kernel. So let me also create another terminal and drag that terminal down here at the bottom. So what we are going to now do, I'll just kind of, lay out some rules. So here we will kind of build and load our module from this window, and this is where we'll run ls mod and investigate, how it can help us. Right. And this is the first time I'm going to explore a few options of ls mod, and I haven't explored them before, didn't even plan to, or I never had to use them that way. Okay. Anyway, so then let's come down here again. I have hidden the explorer, but we have the make file with us. We have the led.c, and let's go ahead and see first the content of the buffer, the message, and okay, it has nothing, which is great, right? And so now we are going to hit the make command. Our kernel module is kind of created here. Now we have the ko file. So let's do sudo insmod, and what insmod does, we will also explore that in another video, like a dedicated video. So we say insmod ldd.ko, and then once we do that, uh, we'll do dmessage again, and we have this line printed here. Now this tells us, what does this tell? This tells us that the module was processed by the kernel, right? The module was processed. And the other thing that okay, the other thing that we talked about was that the initialization, the init module, so to speak, this function here, this function right here, this could have failed as well. And so if it failed, it wouldn't have returned zero. Because it returns a zero, things are good. Now imagine that after printing this message, there were like certain other steps, and one of them failed, and we had to kind of return like a -1, let's say, right? So in that case, then even though this print is available, this print will still be printed because the print was made at this point, but the module could not load completely because we returned -1. So in that case, the print is available, but the module is not really loaded, right? And in that case, um, uh, how do we confirm that the kernel has actually successfully taken in our module? And that's where lsmod comes in. So let me first show you lsmod. So let's type lsmod here, and lsmod is going to list the modules that are present in the kernel. So if I just typed lsmod and hit the return key, then it says module, the size, and who is using it. So if you see, LDD is the module that we had loaded, as part of this command right here. So that is available here. Is anyone using it? Nope. Nobody is using it right now. No other module is referring to it. And these are like the other modules that are available in the kernel right now. And you can see, for example, this module here has 3 other modules that are using it, right? Okay, perfect. And now just keep an eye on this LDD. So what we are now going to do is do the rm mod, and then we say LDD. Things seem to have gone well. In the D message, we see this. And if we do ls mod again, we'll see that our module is not available here. Right? And this is like that acid test in terms of confirming whether our module was loaded successfully and unloaded successfully. So now let me show you another demo. And for that, let me clear the buffer. So our kernel buffer, log buffer is clear now. Let me go ahead and actually, let's write another statement here. Um, hmm, um, mm, Actually, let's not have this. That's all right. Let's do this. Let's have like a -1 being written here. Let's recompile our module. This is recompiled by typing make command, and then we type okay, not make clean, but we type sudo, okay, insmod ldt.ko, right? Let's not hit the return key just yet. Let's go to lsmod and notice again that our driver or module is not available. In nowhere do we see LDD, and now we expect that this will fail, right? And as you can see, it says, hey, insmod error, could not insert the module because operation not permitted. Okay, perfect. And then if we you know go ahead and do lsmod again, we still don't see our module. So in this case, then the module insertion has failed clearly. And now let's do dmessage, and we see that the dmessage did print the message. And if we can connect the dots now, what happened here, what happened uh, you know here, when the ls mod failed, the ls mod, the kernel, it provided our module, the ldd.ko, it submitted this module to the kernel, right, using the ins mod command, right? So the kernel got our module, the kernel started to execute our module. The kernel was happy up till this point. It said, hey, print k, yes, I will go ahead and print it. So it added the line in the buffer. But then at this point, it encountered that, hey, I'm asked to return and I'm returning a non-zero code, a negative number, which means this module has failed to initialize correctly, right? Which means that this module has not completed its setup, so to speak, or the preconditions are not satisfied. And now at this point, the kernel gets to know that, hey, whatever this module is, it cannot be loaded. It returns an error to insmod, and insmod returns back this. It says, hey, error happened, I could not insert the module. But by this time, because this line was processed, the message is printed here. So long story short, the message that we see in the kernel buffer are only an indicator that our device driver, the initialization code, was being processed. It doesn't mean that it succeeded in loading it. The acid test for confirming whether or not it was loaded or accepted by the kernel is the listing of our module in lsmod's output. So I will go ahead and change this back to 0. I'll also make this hello again, just so that we have a different message. And then let's clear this. Let's also clear this screen here. Then I'll do make again. And this time around, I do sudo insmod ldd.ko, and no errors this time because we are returning a 0. If we check our D message, now we see this message appended to the previous messages in the buffer. And if we go and do lsmod, then we also should see LDT available here, right? And much in pretty much the same fashion, if we were to do rm mod, right, then in the output of ls mod, the entry is gone again, and in the D message, we see the message goodbye from this part of the code. All right, this is perfect. And now we pretty much, at the end of the video now, I just wanted to show you that you can use the man command followed by the utility name to kind of get some information about how to go about using it, right? So what we see here is ls mod. It shows the status of the modules in the Linux kernel. That's about it. I was thinking that it will have more options associated with it, like some flags that we can use, but turns out there are no flags with corresponding to ls mod. So ls mod is like the only variant of this command that you can use. There's no ls mod hyphen l hyphen a, none of that nature, just a plain ls mod, just to list all of the loaded modules and the users of the modules. So with this, hopefully you're convinced as to how we can check using lsmod whether or not the kernel has successfully loaded and unloaded our module. Now let's take a look at the insmod utility and what it does. So I have taken some notes here that I'm going to explain because the flow is kind of interesting. So when we say insmod followed by, let's say, ldd.ko, which is the module, right? That's what this line says here. So the first thing that will happen is insmod will call a function called init module, and this function will hint to the kernel that a module insertion is attempted, right? That is what I have written here. Now what then happens is the control transfers to the kernel, and the kernel code, again at this point, when we did sudo insmod ldd.ko, this was from the user space, right? So insmod then, by calling this function internally, what it has done is transferred the control to the kernel space, which is more secure, right? More secure, more privileged, so on and so forth. And within that, then the kernel now knows the name of the module, so it kind of has some hint to what module is being attempted, kind of to be loaded. So the control is transferred to the kernel. Then after that, the kernel calls the sys init module function, and as part of that, it verifies the permission on this module, right? Does the user have the permission to load these, and so on and so forth. Then it also further calls the load module function. And actually, let me, I see that, okay, right here, what I should have done is you know, done something like so, just so that we see like a nice list. And let me just quickly edit this file, and then we'll go back to our explanation. Nice. Okay. So let's just quickly recap. So insmod called init module, an internal function. This indicated to the kernel that a module loading is being attempted. This calls the sys init module, which kind of verifies whether or not the permissions are proper for the user to be loading this, and also on the file, by the way, right? And then further it goes and calls the load module routine, right? And this load module function will now check the sanity of the .ko. The .ko happens to be an ELF file. It's an object file, loadable kernel module file. So what it will do is it will like check whether or not all the data is rightly specified in the header, right? And so essentially just doing some sanity checks on that queue. And then after that, it will create memory in the kernel space. It will carve out some memory region for the code to be copied to. And then again, recall that when we did in Smart, the code was, or this command was executed from the user space. And so now the code needs to be copied to the kernel space, the code from ldd.ko. So space was created for it. And then the kernel copies over that image into the kernel space, image meaning the ko. And then after that, it resolves symbols, right? If there were certain symbols from the kernel that the module was using, then those symbols are resolved, right? And after all of that is done, a reference to this loaded module meaning loaded code and resolved symbols, all of that clean stuff, all of that memory related reference is then returned back to the load module, right? And then that is what I'm listing here, that this the reference, now this reference that the load module returned, this reference is added into a linked list of modules that the kernel is maintaining. And then after that, the control or the kernel then will go ahead and actually call the function that is listed in the module init macro, right? So which is this, right? So the kernel then, after adding it to the linked list, will go ahead and execute this function. And if this function successfully exits, then the module is loaded. Then the kernel will flag that module as active and available. And if something goes wrong, all of this process that we were discussing, all of what is listed right here, if this fails, okay, the color changed. Nice. So if this fails, then the kernel will take it out of the linked list and everything will work backwards, and this will return failure. And insmod will then complain that the module could not be loaded. So hopefully you're convinced that the insmod essentially leads to this avalanche of effect of function calls, and towards the end of that function call, essentially, the kernel has added the reference to the copied code with resolve symbols and so on and so forth to a doubly linked list. Well, actually, a linked list, and could be doubly singly linked, that I do not recall at the moment, but it's a linked list. And in that linked list, the kernel is maintaining reference to this module, the executable code for it. And then after that, whatever was specified as part of the module init macro, that function is called. And if that function succeeds, the module is marked as active. And if it doesn't succeed, then it works its all the process works backwards. The kernel will delete this entry, free up the space, complain back to insmod, essentially, that the process failed, and then insmod prints the message on the screen saying the module loading failed, right? And that's what we saw when we had changed this here to -1, right? So the kernel did attempt to process it, printed this message in the kernel buffer, um, right? And then at this point, the things failed and it worked itself backwards, and insmod had complained to us. So that then is like a hint at some details of how insmod works and why we are using it. In the next one, we'll explore rmmod and other utilities. All right, we are now going to take a look at how the rmmod utility works, and how the kernel kind of removes the module that we have earlier loaded from the list of kernel modules. So we typically call rmmod followed by the loadable module name, and it's typically also called, or we execute this utility with the super user privileges, right? And this is called from user space, right? So that is important. So what happens is, when we call rmmod, it internally calls the delete underscore module function, which hints to the kernel that a module is being attempted to be removed. And so the control goes from user space to kernel space, right? At this point, kernel takes over, and kernel now knows which module we are trying to kind of remove. Then the kernel executes the sys delete module function, right? And as part of this, now it does a bunch of checks. So first off, it will check if the permissions are right for the requester. If we just executed rmmod ldd without the sudo, then the kernel will be like, hey, yeah, you're requesting a removal of a module, but you don't have the permissions, so I can't do it for you. So and if anything fails here, the results go back to rmmod, and rmmod kind of fails to complete the execution, right? So it checks the permissions, and then it checks if any other modules that are already loaded, do they depend, or are they using this module? So that all is checked, and after that it checks whether or not the module even exists, right? And after that has happened, after nothing has failed so far, it will go ahead and call the function that was submitted as part of a module underscore exit, in the kernel, the module code itself. So what do I mean by this? So if we go here, this is essentially the function that we provided as part of module underscore exit. That will be called. So this function will be called, and at what point. So let me kind of undo this, and let's go back here. So this function is essentially part of, or rather this, the function provided as part of the module underscore exit macro, that is the one being called here, right? And at this point then the driver is doing, calling the cleanup function and returning back, freeing up any of the space that it has requested earlier, or any of the bookkeeping logic that it had. It is just undoing all of that. It is also somewhere essentially just cleaning up, just undoing what it had done in initialization, right? And once that is done, the kernel then calls the free module procedure. And as part of the free module procedure, it will, so recall that the kernel had like a linked list of, modules that were active. So the kernel now gets a chance to, perform the process of removing that node. And as part of that, it is going to remove any references that the module was making to the kernel space, as well as the kernel space making to this module. And then after that, it sees if any other cleanup is required, there are any other references or other memory that was allocated. It'll remove all of that. Then it essentially uh, you know removes this module. It kind of unloads this module, and as part of that, it will change the state. Change the state meaning it will mark this module as unavailable, or it will mark it as going out of the list. So it essentially changes the state of that module, the variable that is tracking the state of that module. And after that, it will go ahead and kind of, remove it from this linked list, the pool of the linked list elements, and then it will destroy the memory that it had originally allocated to the code for the LDD um, uh, module, right? So first off, deletes all of this, which is same as unloading or deleting the module. And then after that, whatever space it had allocated in the memory, that is gone, right? So in this way, rm module goes ahead and removes the module from the kernel, right? The space allocated for the executable code is destroyed, and that is how the module gets removed. Of course, if anything fails here, the kernel propagates the error up to the user, and the rm mod utility will kind of print something or exit with an exit code that is not zero, right? So essentially, this is how rm mod works. So now we're going to take a look at the very familiar utility of mod info, right? So mod info, well, right now we don't have any module built, but mod info goes ahead and prints the information that's kind of put inside the module, on the module code by the authors of the module. So in this case, we put in like the description, author name, and license. And as you can see here, these are like the various fields that mod info can read and print. Okay, so what we'll do is we'll make our module here, and when we look at what all it has generated, there are like many more files generated than what we wanted. We only wanted the KO, but it has generated like all of these files. So when we do mod info, in mod info on our ldd.ko, it goes ahead and prints all of this information. Now, few of the things sound or look familiar. For example, the description, author, license, this should look familiar, right? This version magic here, in fact, the name also should look familiar, although we did not list it here. It somehow picked that up, right? And then there is like depends on and this source version that seems like unfamiliar right now. We did not mention it. And then there is also this version magic. So the question now I want to explore is, where did this come from? So now what happens is, if we go ahead and look at all the files that it has generated, notice that in all of these files, one of the files is ldd.mod.c, and the build system kind of, on the fly generates the C file and then later compiles this into the ldd.ko. And within this, then, you'll notice that there is a lot more information, right? And if you also notice here, there is our very familiar init module and cleanup module, and we had called it this here, but something else is going on here. And nonetheless, if you see here, there is some more information. The name has been added, and the version magic has been added, and then also at some point there is the source version added, and that should match with the one that is here. Now, this is what the build system has generated on the fly and kind of appended, and this is essentially where all of this information is coming from. Now, why does the kernel build system go ahead and do this? That's kind of, again, a little bit nuanced, but the build system is built in a way that it appends all of this information to the module that we are building. And you can go ahead and kind of try and search in terms of what all or what all information the kernel adds, and why all the kernel build system cares to generate the mod.c file. And I'll kind of also give you a little more hint at this point. You can go ahead and open up all the other files. The .o files might not open up because these are like binaries or essentially object files, but the cmd files, the symbol, the simvers file, order file, these all open up, and you can kind of as a good exercise, try and figure out what all the content might mean, right? With this, what we're going to do now is conclude this section, and then let's move on to the next one, wherein we implement the file operations within the driver. So we're now going to journey into making our driver more interactive. And in an attempt to make it interactive, here's the kind of end goal that I would like to propose. So we have our ldd.ko, right? And then we load this into the kernel, and we saw that the init and the exit, the init and the exit functions essentially print hello world and goodbye world, right? And now what we want to do is make this interactive. And in terms of making it interactive, what we want to do is somehow do like a read operation, right? And have the kernel module, the ldd, do something, and then as we read it again next time around, kind of do something again, right? And we want these actions to be as simple as possible, so that we can drive the point home in terms of how we interact with a kernel module. Now there are ways in which, well, obviously, the idea is that when all right, I should have mentioned that the partition here is denoting the kernel space and the user space. Right. That's what the partition means here. And well, what I was trying to drive home is we want to take this user space read operation and essentially implement some functionality or some kind of make the kernel module responsive to those reads, right? And then I was going to mention that the in order for us to do read, there has to be some sort of file somewhere on which we can perform read, and this file needs to be kind of observed by or tied to our kernel module, right? So let me kind of just repeat this again. So we want the ldd.ko to respond to a read operation, right? And then we want it to respond to the read operation coming from the user space. And then the question is, this read is on what? It is going to happen on what? And I'm suggesting that it needs to happen on some file, right? And then the question is, okay, what is this file? Who creates this file? And all of that. Now, one of the things is that we would need to tie the Linux kernel module to this file so that, the kernel module uh, catches the operation that is happening on this file system. So the kernel essentially is monitoring this node, so to speak, right? A file system or a file node. So it is observing that, and anytime there is a read and write operation requested on that node or on that file, the kernel understands that, hey, wait, hang on, this is tied to the ldd.ko module that was loaded, and I must go and invoke, let's say, the read or the write and so on and so forth, APIs that the driver authors have implemented. So that's how it typically works. The question then is, what is this file and who creates it? Now there are like bunch of steps involved in creating this particular file. If we want to go create something called a character type of file, right? And this is usually created in the slash dev slash something. There are steps involved in doing this. So what we are going to do is go towards a much simpler file system that allows us to interact with the driver and kind of peek into the operations of the kernel, and that is called the proc file system, right? And the proc file system is very interesting. First off, this file system is called the virtual file system. And why is it called virtual? Because these are not real files. All right. These are not real files. The slash proc the slash proc directory, so to speak, has many file entries, directory entries, but none of those are real. They are, so to speak, logical, they are, so to speak, imaginary. And what happens is, anytime you perform read write operations on those, the kernel essentially dynamically uh, puts or prints some output to the user, right? So if you try and save certain values to them, they are not stored on the disk or in the memory. That's the idea. And when you are trying to read, it kind of prints certain status or information message from the kernel. So the proc file system then, and it's a very special type of file system. Again, it's a virtual file system. No file in here is real, they are just listings. And when you read or write into those, the kernel kind of prints helpful information or takes in your input and passes it on to the kernel module. These are not real files that are saved on the disk. That's the key idea. And why are we wanting to go this route? It's because creating a proc file is very straightforward from the kernel driver. We can just, during initialization, create a file for ourselves and then have the user interact with this virtual file. And, things will become a lot more clearer as we, develop our code. But here's the idea then. What we are going to do is, within the slash proc, we are going to create some file, right? And let me just call that file, I don't know, pajama driver. Let's just call it pajama driver, or we can call it LDD, driver, or LDD file, something of that nature, right? Anything is good enough here, but that has to be within the slash proc. Let's say this file is there, and how we come to this file, I'll tell you in a minute. All right. Now the idea is that the user, right, the user will perform a read on this file, right? And the driver, which is, let me call this ldd.ko. So ldd.ko is monitoring reads on this file. And anytime it kind of, so it is also kind of internally implementing what to do when this file is read, and this is the part we will implement. All right, so anytime the read happens, there is internally a counter as to how many times read was called, right? So we kind of the number of count, or we keep like a count as to how many times read was called, and every time read was called, we implement this variable, so to speak, by one. All right, let's do that, and every time we read this, let's say we print the message as to how many times the read happened. Let's keep that as our end goal here. So we want to perform a read and see some output as a result of the driver handling the read. Cool. So this is what we are after, and now let me just show you few of the header files. Let me show you one header file that relates to this. So we also kind of, which I did not answer earlier, which I deferred for later, was how do we go ahead and create a proc file entry? And the answer to this is that there is a kernel API available, right? There's a function that we can, execute from the during our initialization function, right? From where we were printing the hello world. There, if we go ahead and create a proc file system entry, so that will lead to the creation of this, right? And again, when we come to code, this all becomes super, easy to understand. And then the idea is that we then have to define something called proc ops or proc operations, right? And we will somehow need to bind, we would need to bind those proc operations with this file entry, right, or this node. And once we do that, then like the kernel or kernel loadable module has created a file entry and tied operations on that file entry, and this file we are saying will be within proc, so it's a virtual or like a logical file. It's not a real file that's stored on the disk. That's very, very, very important. All right. So hopefully, if you have been able to follow so far, let me go ahead and bring up a header file, and this header file is available at this address. Let me change the color here. Yes, so it's available at this address, which is github.com/thorwald/linux/blob/master/include/linux/proc proc underscore fs dot h, right? And the fs dot h essentially talks about the file system, the proc file system dot h, right? Perfect. So what we want to do now is scroll down, and you can take a look at this file, in detail. uh, Understanding this, I wouldn't suggest that, or I wouldn't kind of think that you'll be able to understand this in one shot. But let me go ahead and introduce as to what different parts of this file are doing. So this is a header file, and within the header file, what we see here is this proc ops, right? So these are nothing but proc operations, right? And the proc is like a shorthand for operations. And here then we see lot of entries, and each one of these entries are essentially uh, representing a system call, and these are like the operations that can be done or supported on a proc slash proc file entry, right? Entry within the slash proc essentially. So what we are after then is implementing this read proc read system call, right? So we are going to support this, and which means we will need to create a structure, and then within that structure populate this entry, and all other entries then by default become null or null pointers. One other thing is, at this point you should notice that this is nothing but a function pointer, right? So this is a function pointer. And in terms of writing code for drivers, the two things that you have to be absolutely on top of in terms of the C language is the idea of structs, and the second is the idea of function pointers, right? So that's kind of absolutely crucial and critical. Okay, so we are going to implement this API or a function, and then pass that function, somehow bind these operations to the proc file that we will create. All right, now, so this is what we are planning on implementing. And again, as we implement, things becomes more relatable, and you'll understand it a lot better. The question is, how do we go about creating that file entry, the pajama underscore driver? And the answer to that is this API right here, right? This one right here. Okay, let me just scroll that. Actually, I circled the wrong one. So this API right here. Let me change the color. Yeah, this API right here, right? So this API is telling us that it can create a proc entry, and then we are going to provide the name of that proc entry, the slash proc. So this we need not give, but this pajama driver that we were talking about, right? This as a virtual file that we want to create, this name needs to be provided here. Now, these are some other details as to what the mode is and so on and so forth. And if you see here, we are also providing the proc ops, right? A pointer to the proc ops. And what was proc ops? If we were to scroll up here, well, this is the proc ops. And what does proc ops have? It has function pointers or of various system calls, right? So then all of our next effort will come down primarily to implementing this one structure, right? To implementing this one structure. And the second thing it comes down to is essentially creating a proc entry. And where is that function? Yes. So implementing or calling this API. So there are only two things that we need to do. Populate the structure, the proc ops structure, and then create an entry. And the third thing we want to do is essentially write an API, that can be put here, right here. All right. So what we'll now do is head towards that and write some more code and achieve this end goal. Let's explore the proc file system, the virtual file system a little bit. And I'll try to hammer home the point that these files are virtual, and the fact that these are just entries, these are not files on the real disk. That is very, very important. So first off, let's just go ahead and list things within the slash proc, right? And as you can see, there are many things right here. What we intend to do was add another entry somewhere here by the kind of name pajama, let's say driver, right? So somewhere within this ls system, or like listings of the files within this directory, we want to add this entry. And that's what we'll do once we start to code again. um, all right. So what we have here are these various files, right? And these various files essentially, and there are also directories, by the way, right? So there are, drivers. Well, that's one of the files that I know. Then there or directories that I know of, IRQ, file system, dynamic debug, and so on and so forth. Everything in white is kind of a file, right? So the first thing that I want to show you is that in the current directory that we are in, there are these two files, right? And if I were to do file star, for example, I get information about what these files are, right? What kind of files are these? So the make file, for example, is a make file script, and it's an ASCII text. ldd.c is C source and also ASCII text. The question now is, what are the files within the proc file system? right? So I'm just going to then go ahead and do file slash proc, and let me I don't know which one should I pick. Yeah, I'll just pick uptime, right? Or actually, let me go within drivers and then pick RTC, right? So what kind of file is RTC? Well, it's empty, right? There's nothing there. It doesn't specify what kind of file it is, right? It's not printing whether it's a ASCII text or what is it. And the reason to this is this file actually has nothing right now. It only responds the moment I go ahead and kind of try and read it. So the moment I read it, we see that there it kind of prints so much of information, right? It's printing what's the time, then the date, and so on and so forth, all sorts of details, right? So one thing, hopefully, that has been hammered home so far is that when we kind of do a read on this file, right? When we do a read on this file, there is some driver, potentially the RTC driver, that catches this read, and then there is like proc read, uh, system call, and whatever the proc ops that were available or registered within the RTC driver by the RTC driver author, that API is getting called, and that API is the one which is dynamically printing this, right? It's not saved anywhere on the file system, that is. This is not a real file. It's a virtual file, but we can read and write to it. We can perform file operations on it. And so when we try to inquire what kind of file this is, it says it's empty. But when we try and read, it's actually not empty. In the sense, there was nothing in that file because it was a virtual file. Reading that file triggered the driver to go ahead and print this information, right? So this is very, very important, that the proc file system is kind of a view into the state of the kernel, and all the entries there are virtual. None of them are actual files on the disk. That is absolutely very, very, very crucial. And now one other thing that I want to show you, just the last thing, so to speak, we are going to do ls mod, and let's find out if there was an RTC driver. Somewhere there should be an RTC driver, which I am not seeing right now. Um, hmm. Well, I should have tried this before demoing, but I did not. And turns out that there is no RTC driver. So there, well, the driver is not by the name RTC, but whatever that driver is, whichever that driver is monitoring the slash proc slash driver slash RTC file, right? And it has to be one of these files, these drivers, and I don't know which one, right? Or it could just as well be that the kernel is keeping right, monitoring that file and printing that information dynamically. Anywho, so hopefully you're convinced as to proc is a virtual file system. The files don't exist on real disk, but reading and writing to it can lead to interesting prints, and the driver dynamically prints that information. That is the key. And with this, we'll now dive into, writing some code that relates to adding an entry into the proc system. I have trouble closing the video. Let me just stop recording. Bye bye. All right. So now let's try and create a proc file entry, in the sense that we are going to add an entry into the proc directory. And that entry, let's say, is the pajama underscore driver, right? So we want to add this virtual file, right? Virtual file. And again, this is a virtual file. It doesn't exist on the disk. It doesn't occupy any space. It's just an entry, a virtual file. Now, what we want to do is first add this entry, and then the second is associate the read associate, or rather, let me do this, associate the LDD driver uh, with the operations, right? The proc operations, proc ops, right? And once we associate the proc ops, like through the proc ops, the LDD driver, then what will happen is the read and the write on this will be caught by the LDD driver, and it will respond for it. So we're going to add those functions in. So as part of this video, we'll just focus on creating this entry. And as part of like the future videos, we'll go into implementing the read operation, so to speak. All right. So what do we have on the screen here? So this should look familiar. These are like the header files that we have been including. I kind of modified this a little bit to add some information here, and this should also be familiar. I deleted the code within this and also within this, and these are the module init and module exit macros. Now we are supposed to implement something here and something here. So what I'm going to do now is let's kind of bring up the header file, the proc underscore fs header file, and let's look at the proc create. Um, let's look at the proc create function. So this is the function that will be of use to us. So let's then go ahead and copy this and bring it back here. So let me just go ahead and paste it here. What we want to do is assess. Oh, well, how did this open? Okay. What we want to do is essentially assess what all parameters this takes in, and so what all we should be, populating. Right. Okay. So name seems like, well, it looks like a string. So we'll just provide name here. And then this is u mod underscore t, some mode, u mode underscore t. And so we'll need to figure what that is. And then there is this struct proc directory entry parent. Looks like this will be parent of, the proc entry we add here. And then there is some const struct pointer to proc ops. All right. So the operations, as we saw yesterday, or in the, well, I was recording the video yesterday, but in the previous video, what we saw was that the proc ops is this structure right here, right? And so we are supposed to kind of implement the entries within this. So that is like another requirement. So what are we going to do now is we are going to, just because we are trying out things, we are going to set this to 0, right? Just because, okay, I should also mention that if we go back here, the way you can, kind of uh, process and figure out. So what we are going to do is, it on the right side here, GitHub is telling me that, hey, types.h has this u mode underscore t. And what is u mode underscore t? It is nothing but a type def of unsigned short. So because it's a short, what I'm going to do is set it to 0. I don't know what the valid value is. I'll just set it to 0 because I can, right? Now here there is const char star name. So I'm going to, name this as pajama underscore driver. This is where the name goes. And what this name is indicating is, in the um, proc directory, what is the entry that we want to create? And we want to create by the name pajama underscore driver. So that string I'm providing here, right? So the mode is set to 0, whatever that means. We'll see whether or not it works. I'm not so sure on what the parent directory has to be. So I'm going to again set that to null, and I'm going to set it to null just because it's a pointer. And right now I don't even have the proc ops, so I'm going to set it to null as well, right? And so looks like it's going to return something like this, the directory entry. So I'm going to have a static variable for that, and I'll call it what do we call it? Let's call it I don't know, proc entry, right? uh, entry, right? So let's just call it proc entry. This is a static because I just want this variable to be accessed by the entries or functions within this file only, and that is also the reason why we have static here. All right, perfect. So all of this is set. I just have to get rid of all of this, and let's just then go ahead and equate this with this, and then I'm cutting that. And what I want to do is I want to create this entry as part of my initialization function, because remember, when the kernel is loading the module, it will give a call to pajama module and underscore init, and that is where the content within this function will get executed. Now, to be able to detect that we are actually within this driver or this function, what I'm going to do is just write entry slash n, and then at this point I'm going to write exit. So this way we'll know that we entered the function and we exited the function, right? Okay, perfect. And let me also kind of go ahead and align this with the function. Well, let me just align the function parameters. Perfect. So now what we want to do is we have created this proc entry, and actually just because I'm copy pasting my from my notes elsewhere, I'm going to rename this to custom proc node, just so that as the code develops, I can continue to copy paste from the file that I have on the side. All right, perfect. So what is going to happen here is, if this succeeds, it's going to provide a pointer to that node here, and that is used later. And later in what sense? So as we are inserting, doing like a ins mod on ldd.ko, uh, this init function gets called. That should be like absolutely clear by now. And so what we are doing is we are creating this node, we are creating this entry here, right? Pajama underscore driver. And what we expect now is, as we unload our module, as we do rm mod on our module, right, we would want that this entry go away, right? So in order for the entry to go away, what we need is another function that we can call from the exit module, and that has to kind of do with think it's called the remove parent directory. We can use, oh, just a moment, right, we can use this proc remove function, right? We can just go ahead and copy this, and let me just go ahead and paste it here. So proc remove entry, and note that this is like returning void, so we need not catch that return value. It is not going to return anything. Sorry, this is the one. So it's not going to return anything, so we need not catch anything, right? So that's why we have this. And then it says it takes a pointer to proc directory entry, and we have the custom proc here that we got, so to speak, the pointer to the node, right? So I'm just going to, or the pointer to the proc entry, so I'm just going to go and pass this right here, right? And then much like this, what I'm going to do is print that we are in the module exit. And let me go ahead and also do this, um, entry, right? Okay, so this is the important action here, right? Perfect. Now what is worth noting is, we as part of initialization, we are going to introduce a node into the proc entry, and as part of the exit, we are going to remove that proc entry. So as part of this video, we're wanting to just see if we can add this proc entry or not, right? So what I'm going to then do is go to terminal, create a new terminal, and put it on the side here. And then I'm first going to list entries in the proc, And what we should note is the pajama driver, right? The pajama driver, that entry is not seen here, right? It doesn't exist, which is perfect. And now what we are going to also do is uh, we are going to do ensure that our log buffer is clear. So log buffer is clear, there's nothing there. And now I'll go ahead and do make, and something happened. So it's complaining that it cannot find proc remove and it cannot find proc create, which is understandable because I did not tell our compiler which header files to look into. So the header file to look into is this Linux proc underscore fs. So I go back here and essentially add that entry. So we then say, okay, Linux proc underscore fs, and then I'll go ahead and kind of make clean, and let me just refresh. Yes, perfect. And then I'll go ahead and do a make. Now let's see what happens. So it just went through fine. The compilation was clean. We have our ldd.ko available here. Now let's go ahead and do an ins mod on this ko. So ins mod, okay, sorry, this has to be sudo ins mod, and then we say ldd.ko, and it says segmentation fault. So something went wrong here. Clearly something is off, right? Something went wrong here, right? And now what I'm going to do is check whether or not the module was inserted. So I'm going to use um, essentially ls mod, and let's scroll up here. Oh, looks like ls mod is inserted. You know what's funny? It's also used by someone, and we don't know who is using it right now. Okay, so that's the looks like a problem. So what we're going to do is now investigate into what happened here, and so we'll do sudo dmessage, right? We are going to execute this command right here, and oh god, there is so much printed here. Now the prints might vary for you in terms of specifically these prints. These are specific to the cpu architecture that is being used, but something's interesting here. So it has printed pajama module underscore init entry. You can ignore this print. This has to come from this has to do with the fact that the kernel buffer was not completely flushed, and this was like a residual entry from a previous run, so ignore that. This seems or looks familiar, right? Pajama module underscore init underscore or colon entry. Perfect. So we are now going to look for whether or not this function exited, and doesn't look like, right? We do not see this printed, which means something went wrong here and something bad happened, right? And we also see procreate something, which is same as this function, right? And then something, 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 bad things are happening. And uh, what might be happening here, again, this is just my hunch, which is, and again, this is like a biased hunch, which is maybe one of the values here is incorrect. Maybe something was expected, right? And I know in hindsight what is expected here. And let me go ahead and see if I can provide you with some information as to how one can figure that out. Mm, let's see if I can reason about it. Uh, hmm, Something happened here. Code audit. Operation open, something class file, something, something, denied mask R. So somewhere again, given my prior experience with this, it tells me that it should also, we should have also given it the file operations here, or the proc operations, which were listed somewhere here. Just a moment. Yes, proc create. So we should have given the proc ops. So what I'm going to do is copy this, right, and paste it here. So we're going to create that variable, and let me also name that variable in a friendly way. So let's have this, and I'm not going to define a pointer to it. I'm going to define this variable itself, but I'll keep it empty, right? So this is a struct, this is a struct, and what we're going to do is take this struct, and because there was a pointer required here, we are going to provide the address, right? So note carefully what's going on here. We have provided the address of a variable that is of type proc underscore ops. And my hunch was that the create proc here went into or ran into trouble or ran into issues because we had not given this, right? Of course, I'm unable to pinpoint as to, what went wrong here. There has to be some line which says, something was missing, but that's not, there. So we suspected that something will be wrong. I'm pretty sure that a proc entry can be within the parent, so this null should not be a problem. File mode can be 0, so this should not be a problem. So this is the only one that is in my head how I, um, again, based on my previous experience, landed on this. I was looking for something here that would suggest, but there is no hint of that. Okay. So hopefully it's clear as to why we are passing the address here. The address is because this entry here takes in an address, right? Takes in an address here. And that address we can get by having a variable here and passing address of that variable. Okay, perfect. And so now we are going to do something which is recompile all of this. All right, so let me pull this right here. Let me do make clean. Let me do make. Now the thing is, ls mod was showing that our, you know, driver is already in use. And now we are going to attempt to remove it because the previous instance of the driver that we injected, we first have to remove that. So we are going to do sudo rmmod ldd. And there is a problem, right? So looks like we cannot remove it because it's in use. And who is using it? The kernel's using it. It's in like a half baked, or it's like a half loaded state, so to speak. And now what we are going to do is also check whether the proc entry had got created. And okay, I'll just type no, and type pajama. Nothing comes up. I'll just do this. Nope, nothing related to pajama comes here. So obviously the proc entry didn't get created. The driver is half loaded and something went wrong. We saw errors. Again, we saw this, right? All bad things. Now what do we do? And the answer right now is we will need to reboot or restart our machine because the kernel, we have kind of screwed it up. It's in a bad state. And this is exactly why we had kind of, installed multipass and decided to do all our experiments within multipass. Just because if a situation of this nature happens where we screw up the kernel, we should be able to kind of, revive the system. Okay, so then I'm going to do multipass stop primary. That's how we stop the primary machine. And if you see the moment I did that, it's attempting to reconnect, right? Because the connection from VS Code is lost. And now we'll do multipass start primary, right? To kind of restart that system, or boot it up, boot the instance, the virtual machine. So let's see, let's wait for it, starting primary. Let's just give it a minute maybe. All right, done. So it is running, and I can confirm that by doing multipass list. Primary is running here. This is attempting a reconnection. I'm going to again click on this, close this remote connection because it'll take a time to reconnect, and I don't want it to take that much time. So I disconnected it, went to the remote explorers and reconnected back. It asks me for my password. I'm going to give it the password P, and now we are back here. Perfect. So let's first do ls mod. And now if you notice, our module is not there, and which makes sense. Our module was loadable kernel module, and after a fresh boot, the module is supposed to be manually loaded, and we did not load it. So that's that. Perfect. All right. I'm also going to do sudo dmessage. Oh, there are a lot of messages here, because the kernel was booting up or the system was booting up. So I'm going to go ahead and now clean those. Perfect. So now when I run dmessage again, there is nothing. So clean buffer. Perfect. I'm going to do make clean. Everything's gone. Let's do make again. Everything is compiled. Now from the previous run, the only change we have made is this, and there are no entries within this structure. Right? We're just providing it with address of a variable, a struct variable that has nothing, right? Okay, so if we are done with this, we are going to also do ls proc just to make sure there is no pajama driver here. And now I'll go ahead and do sudo ins mod ldd.ko. This time around, everything went fine, or so we think. So sudo dmessage, and looks like, yeah, things are fine. We do see these two prints here, which is entry and exit, which is entry and exit. So this is good. This is great. And now let's go ahead and do well, mod info first. Oh, sorry, ls mod, not mod info, ls mod. And we see ldd. Ldd is not used by anyone, which is a good news. All right. And then we do ls proc. And now somewhere here, there should be pajama driver, which I'm not able to find, but I just found it out and it is available right here. Perfect. So a file entry got created within pajama, like within proc and pajama underscore driver. So again, note that this entry was necessary. This is the syntax in terms of how you'll go about creating that node. And so let's go ahead and run one more experiment, or two more actually. Let's try and read this. So cat slash proc, pajama driver, and it says, okay, there is an input output error, which kind of makes sense because even though we have provided the structure was supposed to have the function that implements what the driver should do once this proc entry is read, and we have not implemented it. So given that there is nothing within this structure, the kernel understands that we haven't implemented that function, and so it doesn't even call and prints this error instead. All right, so can we then echo something into it? So let's say echo slash proc um, pajama driver. No, we cannot even echo into it. Permission denied, it says. And now let's go ahead and try and see if sudo works. No, that doesn't work either. And all of this should point to, or kind of and reinforce that the fact that we are not able to do a read and a write, the fact that the operation doesn't complete in any sense, is because we do not have the proc operations implemented. And what were the proc operations? So if we were to go back, the proc operations were the functions of these nature. So that is not implemented, right? That is important. Now I'll go ahead and do sudo rmmod ldd, right? And then do ls mod. This time around, our module is not available. Let's again do sudo dmessage, and looks like the exit was also called correctly. And then let's do ls in the proc, and our driver entry, the proc entry, is also taken out. So we have then successfully added the entry in the proc system, file system, or the directory, and we have successfully removed it. And with this, which this is like an important milestone, because the next thing we do now is implement the read function. And once we have done that, we'll kind of check whether or not reading that proc file system works. All right. A question that I'm wanting to explore now before we kind of conclude this lesson is, when we provided null here, things went wrong. And our driver loading should have failed very gracefully, and it did not fail, right? And the question is, a driver writer should assume that the initialization of driver can fail at any point. And if it fails at any point, we're supposed to kind of undo, right? Undo things and fail gracefully, right? Just so that the kernel is not left in a bad state. So the thing that we should have done is we should have guarded this function execution and put this here. So if this is null, and the other way to kind of check that, one way is to just invert it, the other way is to do so if this was null, we should have actually returned some sort of a negative number. And again, there are like error codes to be returned instead of -1. That's like the standard practice, but let's just do quick and dirty experiment here. And I don't know if this works, but we'll see. And if this fails, I think it will be a good exercise for you to figure out how this failure should have been handled. All right. So, okay, let's see. We are saying error here. Perfect. And then we return back. Um, let's go ahead and do make clean here. Then do make everything compiles fine. We then do sudo, insmod ldd, and something nice happened here, right? It says insmod error could not load the module ldd, no such file. Okay, that is because I did not use ko, and segmentation fault happened. So something really went wrong, right? And I think I have learned something. So let's do sudo dmessage. All right, same crash, right? So this is bad. So this is really, really bad. Then we do ls mod, and let's see. So same symptom, right? Our LDD module has put the kernel in bad state. And did the proc entry get created? Uh, doesn't look like. I'm not able to find it. Can you find it? Okay, nope, I do not see it. So what really happened there then is the kernel crashed while executing the create proc function, or proc create function, and it did not return back at all, right? So somewhere within the proc create, there should have been a check for whether or not the proc ops is available as a parameter. And if it was not available, it should have returned back a null here, and then we could have checked it here. But we could not do anything because create proc underscore create itself crashed. Cool. So now what I'll need to do is, again, reboot my uh, primary machine, and then kind of go ahead and implement or proceed with implementing the read function. So what I'm going to do is restore this back to the working state, which is this, right? This was working for us. And now what we'll do is we'll go ahead and implement the proc read function. All right, so as part of this video, then we are going to implement the read function related to operations on the proc entry that we had added in the previous video. But the thing is, in the previous video, I screwed up my kernel, landed in a crash state, so I had to restart. And so what I have done is I have stopped my primary instance, and I'm going to just go ahead and restart it again. And once it restarts, I have VS Code here in the background that I'll again kind of connect to the primary machine and then get inside. So let's wait for this to come up, and let's let's in the meantime discuss what we are going to implement. So let me go here again. This is the proc underscore fs dot h. This is the file system or the header file that we are interested in. And within that, line number 29, which talks about the structure proc underscore ops. And in this function, we are wanting to implement a function of this nature. So this here is a function pointer, and the variable that will be pointing to the function pointer is the proc underscore read, right? And so let me just copy this because the signature is important for us. And the multipass has started the primary machine. Yes, it's running. So I'll go to VS Code, then go to Remote Explorer, then go to the IP address, and within that LDT, click on this arrow, and it should attempt to connect. I'll enter my password, and it's connected. Perfect. So this was the code that we wrote last time, and one of the things that I copied now was this, right? So I want to implement a function now which is of this type, right? And I'm going to call it, and let me just cheat here, and I'm going to call it, pajama read, right? And then it is going to have function parameters of this nature, right? And so this, let's say it's going to return 0 because that's success. And much like, the case here, I'm going to put a print statement here, and then put this here. We don't want entry or exit, so this is what we print. Now again, notice that this name here is different than what it is here, but all the other, you know parameters here are essentially same. And I would want to, like, here there are no names to the parameter, which is fine, but I'm wanting to give these guys name. And let me also kind of copy over the names here, just so that our function parameters have a name. And let me also kind of align this right here. And let's put it right here this way. We don't need this anymore, so I'm going to get rid of this. And the other thing I'm supposed to do is, so remember, one of the entries here, and that's what we kind of copied, one of the entries within this struct is the proc underscore read. This is a variable as seen or as available within the struct proc underscore ops. And this variable happens to be a function pointer. So I'm going to take this variable, right, and say, hey, to this variable, I want to assign value of whatever the address of this function is. So that's how we're going to populate it. And let me just go ahead and quickly check if I'm committing a crime here accidentally, because I don't want this to fail. Yeah, this is correct. And well, the thing I was looking up on the side is whether or not there should be a comma here. It's not required. Comma or a semicolon, right? That's not required. All right, perfect. So we have our function here, which is supposed to be kind of called when the read on that proc file, a proc slash pajama underscore driver is called, right? That is what we're trying to do. And then as we are initializing our module here, we are saying, hey, please register the driver underscore proc underscore ops structure as the structure holding the function pointers that are supposed to be called when the procs file entries read or written to. And we can visualize this. So again, we have the proc entry here, which is the pajama driver. This we achieved in the last video. And now what we are doing is, through this we were binding actions on this: read, write, open, close, all of those actions. We were binding what this structure here. We were saying that this structure is going to have function pointer to various actions, right? And this function pointer then goes back to this function. So every time we call a read on this, this function will get called. right? The kernel will understand that this driver has this function which needs to be called every time someone tries to read this particular virtual file. So that is why we are writing or doing all of this, right? And again, once you see the demo, things become clear. What I'm going to do is also make this static. And the reason behind making this static is I want this function to be only available within this file. We don't use it outside of this file. All right, perfect. And now what I'm going to do is, okay, uh, let me close this. The way you open a terminal is go to the main menu and create new terminal, right? And I'm going to drag it on the side. So I'll go ahead and do make clean just because, we want to build fresh, and then let me hide the sidebar. All right. So let's go ahead and try to do make. Yeah, things have compiled correctly. Let's do ls mod to ensure yes, the driver is not loaded. Obviously, let's check on sudo dmessage. A lot of kernel logs here. We'll clear those, right? So that is gone now. And let's also do ls slash proc, and there is no pajama driver here. Yep, not there. All right, now we'll do sudo insmod ldd.ko. Thing seems to have gone all right. We'll do ls mod first. Yes, our driver exists here. And then also go ahead and kind of do dmessage. Very nice. So, entry and exit was called. So entry and exit was called. Everything's great so far. Now we are going to check whether, the proc system has our driver's virtual, file entry, and it does. So that is also good. Now we are going to attempt to read this, and let's see what happens. And before that, this is the D message, and we are going to do cat. So cat is a program that tries and reads the given file. So pajama driver, okay, nothing got printed, which is fine, but at least it exited without errors. So in the last video, it had exited without, sorry, with errors, and the error was input output error, something like that, right? And we are going to do sudo dmessage and notice that pajama read, which is same as this was called. So what we have succeeded so far in doing is, and this is like absolutely crucial, this was our virtual file system. We added an entry, by the name pajama driver here. And then when we loaded the LDD in the init, we created this entry. That was number one. But the second thing we did while we were creating this entry, we said, hey, there is this, there is this struct which is of the type proc ops, and within that, the proc read variable that we are assigning to a function, and that is the function you call when a read operation is performed on this file. And what we saw right now was that we provided a function pointer here, and that function did get called when we attempted a read on this file. And now this is absolutely crucial and very fundamental to how drivers or how the user programs interact with the drivers. The 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 driver is associated, mapped onto a file. The interactions of the driver are mapped onto a file, and interacting with the files from the user space essentially triggers some associated functions in the driver. This is absolutely key. And recall that at some point I was telling the pieces of C, that you would need to know is, structs and then function pointers. Those two things are enough, an absolute mandatory thing, actually. Okay, perfect. So one thing that we haven't answered, right, which you would have seen, is who is passing all of this, right? Why these input parameters and who is passing these? So the answer to this is when the kernel is like hunting down our driver and then calling this associated operations, file operations related functions, the kernel is going to provide, all these information. The kernel is going to provide them. And now in the next one, what we are going to do is we are going to see if when we perform the cat operation here, can we print something in the user space, right? And again, let me make this very clear. So when we perform the read here, the read was happening from the user space. So cat slash proc slash, pajama driver. This was being read from the user space. The read on this was passed to the kernel, and this is like then the kernel space, right? This right here translated into a system call, right? And syscall of what type? Read type. So the kernel caught it. The kernel figured LDD is the driver for this, and then LDD had the proc. And okay, just give me a moment. Let me clear this. Yeah, so we had the proc underscore read here, right, which was this, and so the LDD driver just called this, and then we had the print k, and the print k prints into the kernel buffer. So that is where we see this line, that within the kernel buffer, we do see that the read operation was called, executed. What we want to do is print a message, send something from this back to the user space. And this we haven't achieved. And once we achieve that, what we would have seen is that the driver can pass some information back to the user. And why is this important? Okay, let me paint a picture, right? So the reason this is important is, let's say you have a camera, right, which has taken like a picture of you here, right? And so the camera somewhere is connected to your Linux machine, right? Let's say this is the Linux kernel, and so there is like some CD, the camera driver. And so what's going to happen is there is some buffer here or some memory in the camera itself, and your snapshot is right there. And so the driver, and let's say we have the camera app here, right? The app, and here you click, like you click on the shutter button, and kind of you want to take a picture. So what happens is that action is translated to some system call for the driver. The driver then goes and reads the image here, brings it back, and then it's supposed to pass it back to you. And in fact, the cameras also stream that picture continuously, so they are essentially passing information back to the user space, right? And that I'm saying we haven't achieved right now. We haven't kind of copied content from user space to kernel space, and we haven't copied from kernel space back to the user space. And this copy happens because you don't want them to share the common you definitely don't want the user application to be able to access the kernel's memory space, any memory space that is required or managed by the kernel. Because then what will happen is the application has a hook inside, or like a way to get into the kernel's memory, and then malicious actors can actually write some code that can hijack your kernel, and we don't want that. So what is better is we provide mechanisms wherein the kernel can copy data from user space into its own space, operate on that, and then send it back to the user space. So what we are now wanting to explore is, can we send back some data from the kernel space to the user space? So now we are going to go ahead and kind of implement that interaction in terms of the driver passing some data back to the user. So let's imagine what that means. So we were talking about like reading the proc entry, and then the proc entry was slash proc slash pajama driver. And our idea here was we are going to perform a read on this file, this proc entry, and as a result, it will trigger the pajama read function that is implemented as part of the LDD driver, and that too as part of the driver proc operations here, right? And this is the mapping that we have, and so this function is what the kernel will call, but as a result, or rather this variable, this function pointer is what kernel will call, and it is mapped to this function right here. And in like previous chapter, what we saw was every time we perform this operation, we do see this print, right? And so now what we are going to do is, what we are wanting to do is, we are wanting that this function pass some message, let's say something like so, back to the user, and we will want to have something printed on the terminal as a result. That is our intention. And recall that whatever gets printed here is part of the user space, and the the driver is executing in kind of like the kernel space, right? And so we are now wanting to transfer data back and forth. Well, in this example, we're wanting the kernel to send back something to the user space, the driver to send back something to the user space. That is our intention. And so with that, the question is, how can a driver function like this pass some data back to the user space? And the answer to that is that when this function is executing, when the kernel kind of executes this function, the input parameters here are populated by the kernel, right? Some of them are input, some of them are output, so on and so forth. But this one right here is a pointer that the kernel passes us for a buffer that's kind of in can be read by the user space, so to speak, right? So let's say this is that buffer. So what the kernel will do is pass it as pass it as sorry, my bad, it will pass it uh, let me just erase all of this. Yeah, it will pass it as the user space buffer variable, right? So this variable here will be pointing to the buffer that the user space can read, right? This is the user space, this is the kernel space, and this is representing that the user space can read that buffer. All right. So we are somewhere supposed to use, sorry, not that, but we are supposed to use, this pointer right here and do something with it. All right. So then turns out to implement this message now, we will need a local string. And so let me have that string as character array, and I call that array message. And in that I want to kind of save ack with an exclamation mark followed by a slash n, so that a nice new line is also printed. Okay, so then I would also want the length of this. So I'm going to have, size t length. Size t essentially is same as kind of, unsigned int, so to speak. It's like the standard size that the CPU can handle. And so we are going to just have it as size t. Nothing wrong with making it unsigned int or just an int. You can try those examples. So I'm going to now say, hey, get the string length of the string contained in this buffer called message, right? And so now we have got the size, and the message is also ready. All we have to do is kind of write into this kind of the buffer, or the character pointer. We are supposed to use that and write the characters. Okay, so what I'm going to do for that is I'm going to use an API called copy to user. And copy to user takes in destination, source, and the number of bytes to be copied. right? So what it will do is it will read all these characters, one byte at a time, and it will also copy it over into that user space buffer. So the destination then happens to be the user space buffer, the source happens to be message, and the number of bytes is essentially the length, right? So all right, so we have then we have our message here. That message we are copying over to the user space. And so things look all right now. So let me go to the terminal and do make. So as I do make, it complains, or provides like a warning that I'm not using the return value of copy to user, the success failure, right? I'm not that return value is discarded. So now what I'll do is I'll also go ahead and kind of have int result, and then simply capture the return value in this variable result. Everything else, let's just keep it as is. Right, let me just go ahead and do make clean, then followed by that, let me just do make. And as I do make, this time around, things have cleanly compiled. Perfect. All right. So now first what I want to do is ensure that our module is not loaded already, like from the previous run. So that's not there. So that's a good thing. Let me see if our the kernel log buffer is cleared, and that is cleared as well. Now let's go ahead and do sudo insmod ldd.ko, right? And then when I do lsmod, and I'm going to kind of just grep for ldd, yes, that's available, right? So this was just to avoid all of the noise that this prints. And then you know just straight up we just search for ldd within this list, and we got this result right here. Okay, perfect. So ldd is loaded. That means our proc entry should also be available, right? Yes, pajama driver is available. Now what we want to do is first check in d message. Notice that there are only two prints which relate to the initialization of the module, right? So that is perfectly fine as we expected. And now what we'll do is we'll do cat slash proc slash pajama driver. So our expectation or hope now is, and let me call that out explicitly here. So our hope is we are in the user space, and kernel space is what we are kind of going to invoke based on this read. But we are hoping that the kernel, or rather our driver, will pass back uh, you know this message to cat, and cat should print that, right? And one more thing that I should highlight, and let me just quickly do so here. This is just like a pure FYI. So the ACK here is an array of characters, right? And there are six of those, and the reason why it is six is what I want to explain. So we have this and then this, right? So this is not shown here, but a string is terminated by a slash zero, a null character. And all of this you see here. So the length of the string is actually six. That is important, right? 1, 2, 3, 4, 5, 6. And as you see here, 1, 2, 3, 4, and 5, because the sixth character is hidden. We don't see it, but see, the way it treats strings are terminated. These are character arrays or character sequences terminated by a slash zero, a null character. Okay, so then what we are going to expect is this, right? This message right here should be printed by cat. So let's go ahead and execute this then. And nothing happens, right? We expected that ACK be printed, but ACK is not printed. And so what is going on? So we do sudo d message, and we notice that this print right here, the pajama read, well, that is coming from here, which then means that all of this actually executed, right? And if all of this executed, now why is cat not printing anything? Well, the answer to that is we are supposed to return back the number of bytes that are returned to the user space, and the number of bytes we are writing is len. Right? We're writing these many bytes. Now, the other thing is cat will, once it knows how many bytes have been returned, or in the user space how many bytes are copied over, so to speak, it'll then go ahead and read through that user space buffer and print it onto the terminal screen. So let's then, first off get uh, our module out, right? So I'll just do ls mod grep ldd not found, great. And then I'll also clear the kernel buffer. So kernel buffer is also clean now. Let's go ahead and do that again. Yes. And then I'll do make clean. Right. So now let me compile our code with this one change right here. Right. So let me go ahead and do make. We'll repeat, sudo insmod ldd.ko. And then I'll repeat this module is loaded. Now let's do cat proc pajama driver, and something happened, right? Something bad is happening. It's never okay. All of a sudden, it's printing so much, right? And let me kind of kill this by Control C, doing a Control C. So ACK is essentially printing just too much to the point that it has frozen my virtual machine, right? So what is going on? And well, looks like okay, I'm in a very bad situation right now. So okay, great, my system seems to have recovered. So something happened here. We did see the message getting printed, we did see this getting printed, but it was continuously getting printed and we didn't want that. Now the problem is cat is printing the same information again and again too many times. And why is that happening? Right. So let's just go ahead and do sudo dmessage, minus, well, maybe not minus c, but dmessage. And we see that the pajama read is getting called too many times. Right. It's just going on and on and on and on. So the reason to why this is happening has to do with the fact that we are returning length. So the way cat works is that it is going to continue to read a file until it hits something called end of file, right? And it knows it has hit end of file when the number of bytes read or written into that buffer is returned as 0. And this is also why when we did not have the length here but had a 0 here, a cat would not print anything, because it was like, hey, 0 bytes are returned into that buffer, there's nothing for me to read. So what we would now like to do is convey to cat that it has read all of the information that we wanted to pass. And the way we go about doing it is we say, hey, you know what, this offset right here, this is the offset from which the subsequent reads happen. So first time when cat reads, we return it 6 bytes. So next time when cat reads, okay, let me just explain this little slowly. And we are trying to explore the use of this offset keyword. This happens to be an um, input output type of variable, because we can consume that value, we can also kind of write back that value. So from that standpoint, this variable can be used as an input and output. All right. So think of it this way, that we had too long a message here. Maybe we had something that was 1024 bytes, for example, and we chose to copy maybe, I don't know, maybe let's say 1 byte at a time, right? So now the question is, every time we just copy, so we are providing 1 byte here, and we are providing here msg in brackets, we are supposed to then kind of read an offset, because first time we'll copy this value, second time we are supposed to copy this value, so on and so forth, 1024 times, right? Each time we are copying 1 byte. So now the thing is, on a subsequent read, we'll need to read this again. We'll need to call this function in that case 1024 times to first off read all of that information. But the problem is, every time we call, we would also need to keep track of what index we are supposed to read from, right? And that is where this offset comes in. So if we update the offset on every call, right, in our case by 1, let's say, then what will happen is on subsequent call, we can use msg, some syntax like this, to be able to kind of progress forward. I hope this is making sense. The idea is that the offset can be used to keep track of where to read information from on subsequent calls. All right, and this will make more sense when I talk about why cat was printing the ACK message again and again. So here's what was happening. The value of this offset by default is 0, right? If you don't modify it, the kernel just sets it to 0 and lets it be. The first call that the kernel initiates to this, the value of this, right, or the content of at the location of this. Okay, my ability to spell is just horrible, and just stay with me for a minute. Things will become a lot clearer. So offset, when we dereference offset, the kernel has set the value of this to 0 for the first call. And the reason to that is the kernel knows that you will read in your from your local buffer wherever this message is. So this is our local buffer. So you will start to read from the 0th location, so on and so forth. Now, first time when this function is executed, we have read until the 5th byte, right? And that's how we have read a length of 6. The question then is, because cat got an answer 6, cat kind of printed the ACK message on the screen, but then because cat did not see end of file character, or it did not see that there are no more bytes to be read, it gave a call again, it issued a read again. And at that point, because the offset was 0, we started to read from the 0th offset again. What should have happened is we should have tried to read from here, or we should have said, hey, we already wrote whatever we had to the user space buffer, and there is nothing else to be written, and so we should have returned the value 0. Once we do that, cat kind of gets to know that, hey, I read all the 6 bytes that were there, and there is nothing else to be read, so I can finally print this message and just exit, right? So all of this will make sense once I type in the code, and the code is this. So we were supposed to first off update offset by essentially the length. So, you know, so it's like next time around when the same utility is calling, wanting to read the buffer, continue to read the buffer, we are supposed to read from, or rather skip over what we read in the first time and then start reading from the updated offset, right? And there has to be like a star here. All right. And now here's the thing. We would need to check that if this offset is beyond the length, then we want to return 0, because there is nothing to be, uh, you know, read essentially. Right? And let me actually print this right here. Oh, actually, not here. Let me go ahead and print it right here. Yeah, that way we know. Right. And at this point, then we are returning length. At this point, when the offset crosses the limit of the length, we say, hey, there's nothing else to be read here. Let's just go ahead and return a zero, right? And now the interesting thing is, um, we can do this check on the top, right? So let's just do our check here, and then let's say, hey, if offset is greater than or equal to length, because if we have okay, this might become confusing, but stay with me. So we had six six bytes to be read. So what will happen is the first time this value, right, is set as zero, so we come down here, we see that okay, this is definitely not greater than length, so move on and actually do the copy, right? So the message, all these 6 bytes are copied over to the user buffer. Now once that has happened, we say now update the offset to the new value of offset plus equals len. The len happens to be 6, offset happens to be 0, so the new value of offset is 6 because offset equals offset plus len, so 0 plus 6, and that's 6. Now next time around, cat is again trying to read this to get like more information. The value of offset this time around is 6, and now we are saying, hey, the value of offset is actually greater than or equal to, in this case it's equal to len, so we just return from here. We do not even attempt to copy anything, right? So that is why we have it up there, just to avoid kind of multiple calls from cat. All right, so let's go ahead, do make clean, do make, things compile fine. Now we are going to do sudo insmod ldd dot. Oh, actually, other thing, before all of that, let's ensure that our buffer is clean, right? So buffer is cleared now. We don't have the module inserted, it's already inserted. So let's take it out. Right, perfect. Let's clear the buffer again. Right, let's check. It's not there. Very nice. So let me just do make clean and make again, just so that we're dead sure that this is the code that is going to get executed. And now let's do sudo insmod ldd.q, right? And then sudo d message, yes, initialization worked, ls mod grep ldd, yes, our module is loaded. Now I'll do cat slash proc slash pajama driver, right? And we only get ag this time, and it only is printed once, and no more repeat prints, and things are all good, right? And I'll go ahead and do demessage, so we see that the read happened twice. So the first time it happened, this is important, right? So the first time the read happened, there were 6 bytes that were copied. The second time, when cat called it again in an attempt to read more data, we said, hey, you actually already read whatever there was to read, and we are passing 0 to you. So 0 was passed here, and that's where cat inferred that okay, the buffer is completely read, I have read the file that I wanted to, and things are all good. And that's where it kind of just printed ag and exited, right? Okay, so now what do I want to do? I want to execute this once again, and you'll see that again 2 times cat has called the read, or rather it resulted in pajama read being called twice, right? Perfect. So with this, we have achieved our goal of reading from, or rather interacting with the kernel module and having the kernel module pass something back to the user, right? So what we'll do in the next video is write a Python script to attempt these reads, and then we'll kind of go towards how you can do writes. Okay, so now let's take a look at how to write a user space app, like a very simple app, a Python script that can kind of interact with this driver. So this is from our previous run. Let me go ahead and first, do all the basic stuff. Ls mod. Let me just see if we have LTD. Yes, we do. So sudo rm mod LTD. Modules removed. I want to also clear all the kernel buffer messages. So that's clean. Okay, done. And then let me do make clean. Perfect. All right. So we are in a clean environment now. And what we intend to do is write a user, so to speak, a user app .py file. And this py file is a proxy for an application that wants to go interact with the driver. And so let's kind of define main here. And right now, let's say it returns kind of nothing. And then what we want to do is call this function, right? Okay, so this is, and let me just go ahead and first do like print very quickly, make sure that this is working. So I'll do chmod plus x python, okay, user space dot py, then this executed. There is, wow, okay, there is syntax error. How can that happen? um Unexpected token. Okay, line number one, unexpected token. What's the problem here? Syntax error. Okay, let me, this is stupid. I cannot even write like a function in Python. Let me just quickly, don't judge me for this. uh yeah, looks all right actually. Hmm, what happened here? Syntax error near unexpected token. Okay. It's a py file. Let me go ahead and try actually executing in Python. Oh, we don't have Python installed. So let's go ahead and install. Okay, we had Python 3 installed and not Python 2. So let me go ahead and call Python 3. Yes, okay, perfect. It prints hello world. So, okay, our app is all right here. Now, what we want to do is we want to open our proc file from here and then kind of read a line out of it and then print that line. So let me quickly go ahead and copy paste the code for it. And the code for it is right here. Okay, let's see what's going on here, right? So what is happening is in this main function, we are saying, hey, open this file slash proc slash pajama driver. And after that, read this, in this variable, perform like a line read, right? So read one line, right? And once you've read one line, go ahead and print that line and close this driver, right? And then just simply return. So this is then the very bare minimum, like a basic user app that can interact with the user, that can interact with the driver. So let's then first go ahead. By the way, if I try and execute it, we should run into an error that there is no file of this nature, which makes sense because the driver is not loaded. So I build the driver. I do sudo insmod ldd.ko. Then I quickly check whether or not, yes, our driver is loaded. And now let me execute this app. And as you see, it prints the message that the kernel driver has returned as part of reading a line from the slash proc slash pajama driver, right? So this then kind of, concludes our journey in terms of writing a bare, like a very bare minimum driver and then having it interact with the user space, right? User space application. And we only kind of, journeyed through using proc read as our example. And now here's the challenge for you. What I would want you to try and implement is we explored the path upwards, which is read, And now my challenge to you is, can you implement the path downwards, which is right? And the challenge for you then is, can we do this? Can we have an empty buffer, right? An empty buffer in the kernel space as part of our LDD driver, much like how we had the MSG. Let's assume we have a global MSG that is, let's say, 10 characters long and is essentially empty. There's nothing there, that buffer is empty. What I would want you to do is implement the proc write function, so that when the user attempts a write, this function gets called. And as part of that function, take inputs from the user and write them in this buffer, right? And the next time around, when the user performs a read of this nature, read line or cat, then pass back this message. So essentially, can you implement a driver that echoes the writes done by the user every time they perform a read, right? So on so let's say if we were to do something like so, echo hey to slash proc slash pajama driver, every time we kind of do something like so, let's say, kind of we write hey into pajama driver, this hey should be stored in the buffer right here, or this buffer right here. And every time someone performs cat slash proc slash pajama driver, then they should see hey printed back. Instead of the ack here, they should see hey. And so that is kind of the challenge for you. All right, so we have reached the end of the course. And again, what we explored, let's just kind of, very quickly go through all of that. So we saw as to how to write a device driver, right? And we focused on using proc as, the file system that we interact with, right? Then as part of writing this, we understood the compilation process, how the module gets compiled. Then we saw how to load the module, unload the module, right? And then we looked at other utilities that help with debug and analysis. We looked at all of that. Then we looked at how to go about actually implementing. Well, actually, let's put it this way. We looked at the basic components of the driver, right? The init, the exit, and then after all of this, we looked at system calls, and specifically those that relate to file operations. And the file in our case, or the file system in our case, was again proc. I just have to reiterate, this is not a real file system. There is no block of memory associated with this on the disk. It's virtual. And then we looked at how to create proc entry, right? And how to interact with it. And as part of that interaction, we looked at the read system call, right? And then towards the end, we explored interaction of user and kernel space. So this is kind of what we looked at, and trust me, this is what every kernel driver has. Boils down to this pretty much. And let's talk about what we have not taken a look at, and what you can kind of try and explore on your own, or follow along in the next course that we plan on releasing on the Linux device drivers. So what we have not seen is, the character device driver, and how to actually create like a node within slash dev. We haven't seen at how to go about implementing other system calls, right? Open, close, read, write, those kind of things. And most importantly, we haven't looked into, so if this was our Linux kernel, we haven't looked into how to actually go about, controlling or interacting with an hardware. Let's say an LED, for example, or a switch. How can we have the Linux kernel module interact and handle actual hardware that we haven't seen yet? Then we haven't seen, kind of uh, modules that are preloaded in the kernel image. What does this mean? So this means that as your system, like the Linux kernel boots up, your driver should be already part of it. That exploration we haven't done. We haven't also not looked at something called um, device tree, right? And the link of device tree to the module, we haven't looked at that. And there are, of course, many more things, but knowing this in addition to what you already know can actually get you to a comfortable start on a device driver's team, where you wouldn't be asking basic questions to the senior team members. Rather, you will be ready to fire and ready to contribute, to the point that you can actually deal with hardware. With what you have studied in this free course, you'll of course be able to kind of absorb more information from any of the seniors on your team. But with the next version or the follow-up course on the Linux device drivers, you'll be able to go down and control the hardware, right? And so with this, then I hope that you enjoyed this free course. And if you like this course, do leave us a feedback, do rate the course. And I request you to kind of spread it around in your peer group also. And with this, I'll see you in the next one. Bye bye.